young generation of scientists presenting very high quality research, productivity, and potential impact of their research. It was really very impactful, very exciting to see. And today, I think hope this is going to repeat, and we're going to see another very exciting topics presented by emerging scientists who are representing the next generation of our scientists, of our engineers. So look forward to the next speakers today. To the audience, I'd like to say, pass my regards. Hope that they get inspired by the potential of the research that we will see today.
Okay, thank you, Professor Azaka. So, Professor Jamin Tao, so welcome to say something to our audience.
Okay. Good evening, ladies and gentlemen, especially for all the audience in Qingdao City. I'm not familiar with Qingdao, of course. I went to Qingdao many times. I do have many friends in Qingdao. And this time, I think it's very interesting show, online and offline. And the company is also very interesting, right? How to see the new thing for scientists. Anyway, this year, this special form for scientific exchange or scientific companies. It's a lot of experience. And I know Qingdao is very good city, and during the past maybe 20 years, the science and the technology study and the high-tech industry in Qingdao get progress very fast.
Yes.
And there are a lot of new companies and new research results in Qingdao. And Qingdao for science and technology in China really become more and more famous and more success. And last time we had 5-10 scientists, young scientists in Vietnam talk, and I hope next all of the speakers will be very successful, and I wish. And next time, and for maybe from now, we can have such kind of scientific forum and exchange and activities, both offline and online, more and more in China and all around the world. Thank you. Thank you very much.
Okay, great. Yeah, Professor Cao, you mentioned, yeah, very important things. Qingdao is very, nice city for innovation. There are a lot of industry, a lot of academic societies. Yeah, they're waiting for you. So we hope next time we can have you here on site. Okay, Professor Jagdish. Yeah, hello from Qingdao.
Hello.
I think you
Hello.
have been here before. Yeah.
Yeah, sure. Yeah, good. Okay. Thank you very much, Alice. And and it's a great pleasure and honor for me to be here. And iCANX has done a fantastic job in terms of organizing these talks and bringing the global community together. The beauty of science and engineering is that there are no national boundaries. We can all work together and collaborate with each other and then make progress in science and technology. And particularly, I'm very pleased to see that so many young scientists are participating in this particular meeting. And also that the talks last week we have listened to, they were fantastic talks. And in fact, it was a challenging task for the judges to be able to differentiate between among these so many excellent talks who are going to be the winners. That's been a very challenging task. And good news is that having so many bright young people working in the field of light science and applications. And I think the field of light is in good hands. And then I'm sure that these are going to be the future leaders of our field. And I want to congratulate them for being the finalists for this competition. And I'm very much looking forward to today's presentations. And I'm sure that they're going to be an exciting and interesting presentations. Very much looking forward to it. And thank you very much, Alice and Chenji Gao and the Life Science Applications for this great opportunity to participate in this important meeting.
Okay,
Shishi.
thank you very much. Yeah, it's very great. Yeah, I know now it's pretty late in Australia, almost midnight. So I'm glad you're still there waiting for this event. We continue that. Dr. Anju, yeah, are you ready? Yeah, say hello from New
Yes.
York. Yeah, there are a lot of people
Hello.
waiting for you, the welcome message. Please say something for the, innovation and to the young generation. Yeah, your turn.
Yes, thank you. Thanks. I'm also very excited to be here for the second round of the competition. As Jagadish said, this is a very impressive range of great young scientists. The first round was really impressive. It was very difficult to sort the 5 speakers, and also I'm sure these next 5 will be as good and very exciting science. The field is very exciting also for technology, as was already said, and we have a bright future as a community. Also, it's very impressive that despite all the challenges of COVID and the pandemic, we're able to get together, and technology helps, but also in very different time zones. Here it's just past 8 a.m. But good evening, everyone. They are in Asia, and I look forward to the talk. Thank you.
Okay, great, Andrew. I hope everything is will be come back to New York. New York will come, back to a beautiful city. Yeah, I think in the near
Absolutely.
future, yeah, we can, meet each other sometime. Yeah. So Professor Chu Min, yeah, please.
Yes.
Yeah. So Chu Min is from the Westlake University. I think most of you heard about this university. It's pretty new university. It's for innovation. So Professor Chu, please.
Yes, good evening, everyone in Qingdao and also our panel fellow members for the Rising Star of Light competitions. As all the panel members already mentioned, last Friday, the 5 speakers, 5 talks was really fantastic. And I'm really looking forward to the talks for today. And I really think this event will really become a great one. And all the speakers, all the job have been done by them. It's really great. And I'm really happy that we have so many great participants, also scientists, young scientists in the field of photonics. I wish them the best, and I also look forward to the winners for this event.
Yes, everyone was looking for the winners. You know how many attendees we have last week? We have 300,000, attendees online. So today I think will be more because today on site we have about 400, attendees here. So everyone is looking for that. Everyone is looking for the final results to see who can win the title, who can be the rising star of light. As a word I said at the very beginning, why we start this rising star of light? Because we think all this young generation will lighting the whole world. So yeah, Professor Ren Ma, are you ready? Yeah. So please go ahead to chair the session of rising.
Yes, I'm ready. Could you hear me? Yes. But now I cannot open my camera. Hi. I guess right now everything getting better. So hi everyone.
whose frequency can be precisely expressed in this formula, where frep is the repetition rate describing the mode spacing between two adjacent frequencies, and f0 is the frequency offset from 0. As you know, this expression is the frequency comb spectrum, and therefore, this type of frequency combs is called microresonator-based Kerr frequency comb, or sometimes simply called microcomb. It was found very recently that one can operate a microcomb in the fully coherent regime, which is called dissipative Kerr solitons. The dissipative Kerr solitons are traveling pulses circulating in an optical microresonator. Analytically, you can describe this nonlinear driven system by the Lugirato-Lefebvre equation, which describes the interplay between anomalous dispersion, Kerr nonlinearity, loss, and gain. On the particular situation, the nonlinearity and incompensated loss, there's a solution which is a traveling pulse with a CW background. And this is the Soliton solution. And the whole spectrum consists of equidistant grid of lines, and the envelope is a perfect Sesh profile. The Soliton features ultra-narrow bit-node signal and high coherence, thus is desirable in nearly all applications using microcombs. Now, so far, microcomb has been demonstrated in a wide variety of material platforms. For our research, we built photonic integrated circuit using silicon nitride. The advantages of silicon nitride include wide transparency window from visible to mid-infrared, high Kerr nonlinearity, but simultaneously weak Raman and brane gain. It has a large band gap of 5 electron volts, which made this material immune to 2-photon absorption in the telecommunication band. Also, the fabrication process is CMOS compatible, and you can have a robust bus waveguide to ring resonator coupling. And you can also apply dispersion engineering that you can alter the waveguide geometry to tailor the group velocity dispersion. Next, I will show you the silicon nitride fabrication process developed during my PhD work. To fabricate the silicon nitride photonic integrated circuit, we developed and optimized the photonic Damascene process over the past few years. In this process, we use this process was actually inspired by the Cooper dual Damascene process, which people use to make a Cooper interconnect circuit. In this process, we use standard CMOS technology, such as deep UV stepper lithography, dry etching, low pressure chemical vapor deposition, chemical mechanical planarization, and thermal treatment. I should mention that all these steps are implemented in our EPFL clean room facility. This chart shows our silicon nitride microresonator Q improvement or loss reduction with our progressive fabrication process, together with the result from other groups. Since the first low-loss silicon nitride photonic integrated circuit demonstrated in Professor Miha Lipson's group, with the continuous effort from the entire silicon nitride community, today people are routinely able to achieve more than 10 million Q factor of the microresonator. To estimate the loss of our silicon nitride microresonators, we measure the line width of microresonator of more than 10,000 resonances and analyze their statistical distribution. As shown here, we have achieved intrinsic loss of 6.5 megahertz, and this corresponds to a Q factor of 30 million and the linear propagation loss of 1 dB per meter. This value, I think, is so far the record value for any nonlinear photonic integrated circuit. We also start the yield and the reproducibility of our high-Q silicon nitride fabrication process with 4-inch wafers. Here, I show the design of our photonic integrated circuit on a 4-inch wafer. We use deep UV stepper lithography to pattern the circuits, and compare with the commonly used E-beam lithography, The deep UV step lithography is more stable, more reproducible, and faster. The waveguide roughness is also better. Now, for photonic design, actually 16 chips per exposure field. Here we use a reference design, which is C7, and this design is to monitor the performance variation over the wafer scale. We measure this chip at different position over the 4-inch wafer and compare their performance. As you can see here, we can achieve 6.5 megahertz line width in nearly all the exposure fields. This means that our process is wafer scale reliable, high yield, and reproducible. We can generate more than 160 chips usable per wafer, and the fabrication time is about 4 weeks. This slide shows the summary of the microresonance performance fabricated using our Damascene process. Meanwhile, I want to also show you our progress on low-loss meter-long waveguides. Here I show the photo and the loss calculation data for half meter, 1 meter, and a 1.4 meter long waveguide. For 1 meter, that we can achieve 2.4 dB per meter loss. For half meter, we can achieve 1.7 dB per meter loss. This waveguide can be useful for many applications, such as second harmonic generation, traveling wave parametric amplifier, and true time delay lines. With these high-Q microresonators, a recent breakthrough achieved during my PhD is to demonstrate Soliton microcombs of 10 and 20 GHz repetition rate. I should mention that this has been a long-standing major challenge for the entire integrated photonics community, as high Q is notoriously difficult to achieve in centimeter scale device. Here I show the Soliton microcomb spectrum of 10 and 20 GHz repetition rates. We only use 38 milliwatt power to generate the 20 GHz solitons and 56 milliwatt power to generate 10 GHz solitons. Meanwhile, within the 3 dB bandwidth, there are the 170 comb lines for the 20 GHz soliton and more than 300 comb lines for the 10 GHz soliton. These solitons can be useful for high spectrum efficiency telecommunication systems. Another application that we can use these microwave solitons is to generate the microwave photonically. The principle is showing here. We need a CW which is coupled from a laser to the photonic chip, and we generate the solitons in the microresonator. At the output, we filter out the CW pump and photo detect the soliton repetition rate, which output a microwave carrier at the soliton repetition rate frequency. In such a way, we generate low noise microwave signal in the X and K band using soliton microcombs. We also characterize the phase noise of the microwave carriers. The phase noise value at the Fourier offset frequency are shown here. As I have shown that the soliton generation threshold power is significantly is only tens of milliwatt power, which is already affordable for integrated laser. Therefore, we work on hybrid integration of compact chip laser to our silicon nitride chip. To make a compact device, we need to use a laser self-injection locking, which is the interaction between the laser and the microresonator via optical feedback. The laser self-injection locking has already been studied by OE Wave back to 2015 using magnesium fluoride crystalline microresonators. In this case, a CW light from a DFB laser chip is coupled into the microresonator via a prism coupler. Note that there's no optical isolator between the laser and the microresonator. Therefore, the light can propagate bidirectionally. The light is coupled in the forward direction. However, due to the surface and bulk scattering, there's a tiny portion of light which in the back reflection, which is sent back to the laser. This backscatter light can trigger the laser self-injection locking that modifies the laser line dynamics. In the end, the laser line width reduces significantly. The line width narrowing factor is proportional to Q over QL, where the Q is the quality factor of the external micro resonator, and QL is the line width of the laser cavity. I should mention that the line width narrowing is not due to the external filtering, as the actual laser line width can be significantly narrower than the line width of the micro resonator. When the laser self-injection locking happens, one can increase the power, laser power, to also generate a parametric oscillation, which in the end generate a soliton microcombs. Therefore, using laser self-injection locking, one can get two benefits, a narrow line width laser and a soliton microcombs. And this has been also observed by OE-Wave and the Russian Quantum Center. We also perform this with our silicon nitride device. In this case, we use an indium phosphide laser diode, which is butt coupled to our silicon nitride chip. Initially, the laser diode has a multimode lasing, and the laser line width is brought. By changing the current to the laser diode until one mode coincides with the resistance of the micro resonator, the light is coupled into the resonator and triggers laser self-injection locking. Therefore, the multimode laser diode becomes a single mode laser, and the line width also gets reduced significantly. Recently, in collaboration with Russian Quantum Center, we further studied the soliton formation dynamics in the nonlinear self-injection locking region, both theoretically and experimentally. Meanwhile, in collaboration with Professor John Bowers at UCSB and with Professor Kerry Vahala at Caltech, we made a compact photonic chip which has a fiber output, and the entire device is electronically controlled. In the meantime, we discovered a turnkey operation of solitons due to the laser self-injection locking that could significantly reduce the soliton tuning procedure. In the last part of my talk, I want to briefly show you a recent result in which we built integrated acousto-optical modulator on silicon nitride photonic circuit. This result is achieved from a fruitful collaboration with Professor Sunil Bhav's group at Purdue University. This is the fabrication process flow. Here, we build piezoelectric aluminum nitride modulator on our Damascene silicon nitride photonic circuit. Aluminum nitride is widely used in the MEMS community for microwave and RF oscillators and filters. This is the optical micrograph showing the disc-shaped aluminum nitride modulator covering the silicon nitride waveguide. And this is the SEM image showing the sample cross-section. As we use thick silicon dioxide between the optical waveguide and the metal, the high quality factor of 20 million is maintained. This is the key for soliton generation. This slide shows how the device looks like. When applying an AC driving on the aluminum nitride, the stress optical effect or bulk acoustic wave can be induced, which induce the changes in the refractive index of the silicon nitride waveguide. This change in refractive index results in a modulation of the propagating light. If the soliton is generated in the microresonator, then all the soliton combo lines are modulated at the same speed and the same strength. With this new tuning capability, we can control and modulate the soliton state via external RF driving. Here I show the resistance tuning curve versus the voltage applied. The linear tuning efficiency is a 15.67 megahertz per volt. Also, you can see the tuning has low hysteresis and is bidirectional. We can also tune, using this capability, to tune the resonance to a laser of a fixed frequency, and voltage control the soliton state and bandwidth. Due to the piezoelectric and capacitive nature of the actuator, the power consumption here is less than 300 nanowatts. With this integrated soliton control capability, next, we demonstrate a new application that uses solitons for frequency modulated continuous wave LIDAR. The FMCW LIDAR sent a frequently chirped CW light to a moving object and detected the reflective signal. By heterodyne bit node between the initial signal and the reflected signal, we can get the two parameters, FU and FD. With these two parameters, we can recover the profile of the detected signal. Now, compared with the initial signal, there's two differences observed. The delta T is the time delay which allows us to calculate the speed of the moving object. Using Soliton microcomb, we can build a massively parallel FMCW LIDAR. By chirping only the pump laser, all the frequency comb lines are simultaneously transduced to each comb lines. Therefore, by dispersing each comb lines, which manifest as independent FMCW LIDAR, massively parallel data acquisition can be achieved. We use a feed-forward scheme to generate the soliton. In this case, we apply the sweeping signal on the laser and the resonance together. And the synchronous tuning is actually realized, and it's important to keep the soliton tuning constant. Therefore, we have a constant soliton spectrum and the pulse power. Here we can achieve a frequency excursion of 20 GHz, which is significantly larger than the soliton existing range. We also perform a proof of concept ranging experiment using our Soliton-based massively parallel LIDAR. We image the logo of the EPFL, and we can achieve 5 centimeter level resolution. This slide shows a number of recently demonstrated applications of microcombs using the silicon nitride chips fabricated by myself, such as reconfigurable microwave filter, millimeter wave generation, astrophysical spectrometer calibration, photonic neural network, mid-IR dual comb spectroscopy, optical coherent tomography, data center, circuit switch. Due to the time limitation here, I cannot go into details. If you are interested, please have a look of the reference here. And thank you very much for your attention. I'll be very happy to answer your question. Thank you very much.
Okay, thank you very much, Junqiu. So now it's time for questions from our judges. Any questions?
Probably I can start with a question. This is Minqiu. I'm interested in your last part of your talk about this frequency modulated continuum wave LIDAR. And what's the accuracy you can achieve to obtain the speed and also the distance for the object you are measuring?
Sorry, what's your question? So the question is the principle or?
No, how accurate you can obtain the speed and also the distance of your object.
Yeah, so we actually, so this is a good question. So actually with this experiment, we can actually get 5 centimeters level resolution. And actually we can potentially increase the resolution. And if we can increase the power, if we use a more powerful laser, that increase our signal to noise ratio. And so basically this experiment is only limited by the signal to noise ratio of our device. And if we want to use a massive parallel scheme, and actually it also depends on how many comb lines that we can use. So ideally within the 3 dB bandwidth, if we have more lines, then this can be, all these channels can be used together, and this will add up the signal to noise ratio. So we did not investigate the resolution of the moving object and the distance, but this is actually for FMCW LIDAR. This is actually there's plenty of room can be improved, and this actually mainly based on the laser power that we can use, and also the data, the signal process technology, the math there.
Okay.
Thanks. Very nice presentation. So can you talk to us a little bit more about the potential lifetime of the Q factors that you observe in these microresonators made out of silicon nitride? So what is the storage condition that you typically have, and do you observe degradation in the quality factor as a function of time, potential humidity, etc.?
Yeah, that's a very, very good question. And I can tell you that actually what we observed here is that actually we didn't see any lifetime degradation here. The reason is that we're probably talking about suspended structure like MEMS or like a microtoroid or micro disc that actually is air-cladded. So basically those devices are very, very sensitive to moisture in the air. And actually, if you have moisture on the air, then you know that actually water will have absorption in the telecommunication band. It will typically have the silicon hydrogen absorption and the water OH absorption. And but for silicon nitride device, and also for nearly all kind of cladded device, actually you have a thick cladding. Therefore, if you have some waters or moisture accumulated at the surface, it's actually very difficult for this hydrogen atoms to migrate or diffuse at the room temperature to few micron. So actually, I have a work with a published about to publish that actually we did monitor the actually Q factor over about 3-4 years, and the case is that we didn't see any Q degradation. But what we know that actually, indeed, actually you have to regularly clean the wafer chip, but that's not for the Q degradation. That's actually for the edge coupling, for the contact.
Yeah. Can I ask? Sorry. What about your noise ratio? You see, it's very interesting method for optical comb, and compared with other methods. What about your noise ratio? I think it depends on your process because you use microelectronics for lithography process.
Yeah, you mean compare with this process with compare this microcomb with other type of microcomb?
Yeah, with other type of optical comb.
So the thing is that for microcomb is that the advantage is that you can actually literally make the device very small. So basically you can see here, and also the repetition rate.
It's good, yeah.
Yeah, and pretty small. And so actually, and also it's actually you can fully control electronically, and it's also small and compact, and also the power is lower. And one advantage that actually I want to show here in this kind of thing is that if you use normal comb that has with a bigger laser cavity, that actually the microcomb repetition rate is about 100 megahertz or to less than 1 gigahertz. And for astrophysical spectrometer calibration, usually the resolution of the spectrometer is about 10 gigahertz. So imagine that you have 250 megahertz line width for the femtosecond modular comb. Then you have to filter out most of the comb lines in order to match to the astrophysical spectrometer. Therefore, microcomb has an intrinsic beneficial that actually its repetition rate is just sitting in the microwave domain. Therefore, you use it for K-band or X-band microwave generation, or use it for astrophysical spectrometer calibration. You don't have extra work to actually to filter out the comb lines. And also for millimeter wave generation, now with extremely fast photodetector, and that typically at 100 gigahertz, and you can also get microcomb also has a number of advantages. And this, I think, is probably the main advantage of microcomb. And what is the disadvantage of microcomb is the power conversion efficiency is low. And this has been a kind of major challenge in this field. But also people come up with a number of schemes to improve it. And so, for example, with active doping and make active device. And I think within this technology, with this, I'm confident and optimistic of the microcomb technology, and I believe that maybe with the next few years, we could see more and more advantages of microcombs in a number of applications. Thank you. Yeah.
Thank you.
We have a few more minutes for questions.
Yeah. Okay, Dr. Liu, this is Jagadish. Could you please comment on the residual stress in various layers when you're depositing these things, whether it be silicon nitride or aluminum nitride, and its impact in the performance of these devices?
That's a very, very good question. And yes, actually, I don't mention this in this talk, but you're absolutely right. That usually you want to get the best silicon nitride from the LPCVD process. However, due to the surface chemical dynamics and the temperature difference at the temperature, deposition temperature to the room temperature, you will have a huge tensile stress in the silicon nitride. And therefore, maybe you don't see my screen, that actually we have to actively make some filler patterns. Wait a sec. So if you see my screen, that actually you see we have this kind of checkboard filler patterns. And this pattern is actually to modify the surface topography of the silicon nitride film, such that the film is actually, the stress is not accumulated over the film plane. So if we don't have this stress release pattern, and then after 500 nanometer silicon nitride, there's a crack everywhere. And this actually reduces the fabrication yield. But with this stress release filler pattern, these trenches, and this actually modified the stress accumulation directions in the plane. And this actually can significantly increase the available thickness you can deposit with LPCVD silicon nitride. So in our experiment, we have not observed the crack in silicon nitride film up to 1.2 micron. By zero crack, I mean literally the crack is zero. So the yield is 100%, not 99%. But I think we know very well of how to manage the stress in the LPCVD silicon nitride film. And for other film, usually the stress is compressive because silica usually have a low thermal expansion coefficient. And the compressive stress is usually much easier to handle compared with the tensile stress.
Okay, thank you very much.
Okay, we have 1 minute for a quick question.
I can ask a question, Yunshu. Thank you very much. This was very impressive. Maybe can you tell us the platform is extremely impressive, and I'm sure it's there is a long time that has been spent to develop this. Can you tell us what has been your contribution in this impressive development of this technology?
Yes, thank you very much for this question. So I can tell you that the photonic damascene process was first developed by my colleague Martin Pfeiffer back to 2016, and this yellow zone is actually is my PhD duration from 2016. Well, I actually started my PhD at the middle of 2016 till today, and I want to let you know that actually this dot, if you wait a sec, let me show you. So I want to show you that actually this dot, and this dot are all achieved by myself. So basically, my main PhD work is just to optimize the process of our damascene process. We optimize the lithography, we optimize the etching, we optimize the stress management, we optimize the annealing, we optimize basically everything. So basically, you can see actually we can progressively achieve higher Q. And I have to say, tell you that actually we are our group is probably not the first one to start with low loss silicon nitride photonic integrated circuit, but we spend a lot of efforts, a lot of resource on developing this recipe. So now we are catching up and probably get probably one of the best results at this moment for silicon nitride photonic integrated circuit for the integrated photonics community. Yes, I hope.
And this large Q,
time is
yeah,
up.
absolutely. And this large Q enables these microcom solitons and then all the applications you showed. Basically, the fundamental issue is to get these large Q factors.
The fundamental, okay. I have a paper that I'm going to, yeah, maybe.
Really short answer.
Okay. We have a paper which going to be is in this paper. Then we are going to probably publish soon in a journal. And in this paper that actually I tell you that how much material limitation is and how much processing limitation is. And I still believe that we can still improve the Q factor by optimizing the lithography and etching and simultaneously engineer the thin film growing process with chemical vapor deposition. And I think there's a lot of things that we can do. And also I mentioned this also in my thesis. So if you have interest that we can discuss offline, I can send you the data and the documents.
Okay, cool.
Thank you.
Thank you, Junqiu. Time is up. Let's move on to the next talk. So the next talk will be given by Sui Yang from UC Berkeley. Ready? Okay, so the title of his talk is Photonic Soft Metamaterials, from Symmetry Control to Quantum Interaction. Hi, Sui, are you ready? You are in muting mode. Okay.
Okay, I'm ready. Thank you.
Okay, cool. Can you share your screen?
Yes. Can you see it clearly?
Yeah.
Okay, cool. Thank you for your introduction. My name is Sui Yang. I'm currently a research scientist at Nanoscale Science and Engineering Center at UC Berkeley. It's my great honor to join this LIGHT forum and share my research. My topic today is about photonic soft metamaterials from symmetry control to quantum interactions. In this talk, I will mainly focus on my recent contribution to the exciting field of metamaterials. I will start with the introduction to metamaterial and introduce what's currently challenging in this field. And I will introduce my contribution of soft metamaterials from symmetry control to quantum interactions, particularly for quantum Casimir levitation. And finally, I will go to my summary and acknowledgement. So light, as we all know, consists of photons, and photon can essentially transmit, encode, and detect information when interact with matters. However, the central question is, can we really control these photon behaviors when interacting with matters? From this simple picture, you can imagine that if we can control the atoms, such as atom composition, position, and coupling between them, we can essentially control the light propagation behaviors. And however, in the traditional materials, the material composition and atom fix, such that we have limited application from traditional materials. So here comes the metamaterials in the past decades. Essentially, metamaterial is a new class of material that can really design, control, and engineer our own atom, which are called meta-atoms. As showing you here in this image, for example, we can really design our artificial unit cells. We can design this meta-atom by any shape, size, and geometry. With this unique capability, metamaterials can really open up many exciting applications, from chemical sensors to energy and communications, and even for some applications not found in nature, such as superlens and cloaking devices. In the past decades, we have seen tremendous progress in this field, and people are looking into many exciting basis metamaterial structures, such as split ring resolator, fishlet, and for the coaxial and hyperbolic design. However, as you can see in this development, all the metamaterial are predefined on the planetary geometry. And after its formation, the property is really hard to change and to adaptable functionalities. And that, because of that, we call this metamaterials hard metamaterials. It suffers from several critical challenges from this scalability to reconfigurability. So how can we really solve these challenges? In recent years, people are really turning into a new phase of metamaterials, which are so-called soft metamaterials. Essentially, this type of metamaterials use colloids or soft solids that couple with metallic or plasmonic particles using the soft matter methods, such as chemical formulation and self-assembly methods that can really solve the aforementioned challenges. It offers unparalleled advantages that in scalability, flexibility, and can be freely casting to any substrate and surface, and provide a flexible platform for really enhance the metamaterial applications beyond tradition. However, with the development of such soft metamaterials, people found that there is a fundamental challenge in this field, which come from the thermodynamics in the chemical process. As shown here, a few work from the prototype soft metamaterials, you can see that it can only produce high symmetry or well-defined symmetry from this predefined scaffold. This is mainly due to the thermodynamic constraint. Therefore, due to this high symmetry constraint, the coupling, electromagnetic coupling between nanoparticles is quite limited. It will limit the essential metamaterial functions, such as engineer the index controllability from positive to negative. Also, from some symmetry breaking point of view, it can limit the application, such as anti-Hermitian coupling. And it also lacks from the adaptability configurations. In view of all these challenges, we have taken a completely new route to design our metamaterial we call it from property determined structure. Essentially, we know that metamaterial have a well-defined optical properties. We use that optical property that as a feedback or gauge that to interact with the chemical bonding between the self-assembly process, that in the end, we can define the metamaterial structures by the property itself. Essentially, we use optical energy that interact with chemical energy that can really transform the thermodynamics. So to illustrate how this idea works, I will use a very simple example that with simple 2 nanorods with the symmetry breaking along the longitudinal directions. These 2 coupled nanorods with the offset in the longitudinal direction, which can give us a very exciting physics and photonic responses, as shown here. So it will not only give the electric response from the coupling, but it can also give magnetic response from this 2 nanorod coupling, and also can generate from this 2 electric and magnetic mode. It can also generate many exciting properties such as more optical magnetism, anti-Hermitian, and as well as index controllability. As you may also notice that from this simple structure with longitudinal symmetry breaking, we cannot make it easily use this soft matter methods. That is due to the thermodynamic constraint. So how can we solve this fundamental challenging of thermodynamics in the chemical process? This slide is showing you that the basic idea that we achieve this uniform symmetry breaking metamaterials. Imagine that we have A and B structures. As we already introduced, with different offsets, the coupling between 2 nanorods is different. Therefore, spectroscopically, they will show response at different frequency. Now, if we excite one of the structure, let's see a B structure in the system, the resonance will generate the hot electron. The hot electron will relax and have a photothermal effect that will dissociate the bonding between 2 nanorods of the B structure. In other words, the B structure which are excited cannot be assembled in the system in the chemical self-assembly process. In this sense, if we sweep the wavelengths, we can control the structure not be assembled and only remain the design structure to be assembled in our system. Therefore, we can achieve a very uniform as well with well-defined symmetry breaking metamaterial in the solution. As you can see clearly in this image, we achieve a very uniform offset of the metal atoms in the solution, and the size and offset are well defined. Not only with that, we can also configure and reconfigure this structure with light. By exciting at different frequency, we can generate a very uniform metamaterial, symmetry breaking metamaterial with different offset. For example, in this case, we can achieve 20 nanometer and 13 nanometer offset of these metal atoms. With such a uniform control, we observe a very distinct spectral response, collective spectral response in solution that has well-defined electric and liquid optical magnetism in our metamaterial. Essentially, this is the first demonstration of reconfigurable optical magnetism directly in solution and collectively. With such uniform control of the metamaterial structure, we can also reconfigure the refractive index by light. We use the case-based spectroscopy can further quantify the electric and magnetic mode contribution of the metamaterials. And from this contribution, we can get a refractive index, can tailor it from positive to negative. At this point, you may ask that, why do we care about this tailoring or reconfigurable refractive index? Why it is important? In the next session, I will use one example that's showing you how this power of tuning the refractive index can really achieve or tailor the quantum interactions between materials. And specifically, I will talk about the index engineered quantum Casimir levitation. To begin with, I will show you a very simple picture that to give you an impact of a levitation. So you're probably very familiar with this magnetic levitation tree technology. Essentially, we can use the huge magnetic field that to levitate our train and such that this train can travel very fast. However, let me ask you one question that, can we really to levitate this train without put any external energy, such as the magnetic field here? The answer is yes. And in the next section, I will showing you that using index engineering that we can really harvesting the quantum mechanical energy from the vacuum. Before delve into the project description, I want to first introduce what is the quantum vacuum energy and what is the Casimir force. So the empty space of vacuum is not really empty as we thought. It's full filled with random fluctuating energy. You can think about this energy is coming from the emitting virtual photons that is determined by the Heisenberg uncertainty principle. In this sense, our space are full filled with this quantum mechanical energy. Now, if we put two metal plates, what will happen in this space? Essentially, if we put two metal plates facing each other, they will confine some of the virtual photon in the gap region. Essentially, you will confine the optical mode, limited optical mode in the gap region. However, in the outside region, there are still infinitely random frequency of virtual photons. Therefore, it will exert the lead pressure acting on the metal plate and push them together. And this force is called Casimir force, and it is intrinsically attractive. And this force is discovered in 1948. Since that time, people are thinking that this force is always going to be attractive. How can we utilize this force that can really to harvesting the energy that can, for example, to levitate things? And since that time, people think this is almost impossible due to the intrinsic attractive nature of the force. However, we have found that this Casimir interaction is essentially, it can be controlled by index engineering. By solving the Lifshitz equation of theory here, we found a non-trivial dependence of the Casimir force on the index. As you can see that we have this three different material, two material with the object and one material with a medium. However, no matter what you change the index between them, you will find that this force can be either negative or positive. Means that this force can either be attractive or repulsive. It can never achieve a point that simultaneously existing attractive and repulsive force at the same time. However, we found that if we coat this object here, for example, the gold here, with a very low index of materials, this suddenly will change the power of index contrast due to the near field and far field phase contrast. We call this is transformative meta-material index design. Probably this is simply coating no index of film on the object. We consider it as the simplest meta-surface design. In this sense, due to a phase contrast between near and far field, the force will become repulsive at near field and attractive at far field at the same time. Therefore, we can stably trap this object in the distance we design. So to showing you how this trap look like, we can precisely quantify the distance of trapping distance of the object using spectral response. Simply because these two trapping gold nanoplates will form the Fabry-Pro optical cavity. From this optical cavity response, we can precisely determine the trapping distance of the object. To show you how the trap is looking like, we have the video to show you that the Casimir stable trap. As you can see that as the metal plate is fluctuating, is constantly moving. However, it's always confined in the two-dimensional space in the optical confined region. And we found that this trap is very stable and it can even last for days or weeks. To come to the summary of my these two contributions, I have shown you that how we use the property determining structure to achieve the symmetry control in a large scale of metamaterials. I will also show you that how we use this index design that we can really harvesting the quantum mechanical energy from the vacuum. And essentially, this work has been selected as a top 10 breakthrough in 2019 from Physics World. And I will also briefly to summarize my other contribution in the field, ranging from the curvature design and controllability of meta atoms to chiral plasmonic metamaterials, and to this fluctuating Casimir force induced heat transfer between the two same films. And with that, I will give my special thanks to my supervisor, Professor Xiang Zhang. I will thank my collaborator and postdoc students at the Nanoscale Science and Engineering Center. I will also give special thanks to my funding agency and thank for the committee and the organizer for this event. I will also thank you all for your attention. I would be happy to take any questions. Thank you.
Okay, thank you, Dr. Yang. Okay, now it's time for questions.
Okay, I have a question. Thank you very much. It's a very interesting talk. You know, these days the net surface and applications it's become more and more popular. And in your talk, you introduced a new method to prepare some softer metal surface. And my question is, what about the accuracy? You know, now for the application of metal surface, basically the most important thing is the accuracy of every cells. And the second is, what about your stability, your soft metal surface?
Yeah, that's a very good question. This accuracy, we have pretty accurate control of this coupling. Essentially, we can precisely control the offset. As you can tell from the collective, essentially the ensemble optical response from metamaterial structures. We have well distinct predefined electric and magnetic responses that is precisely designed at this frequency, which means in this large scale, the collective optical response is also pronouncedly well matched with the theoretical design. Therefore, this precise precision will be good in use our new methods, essentially this property determining structure methods.
You know, such kind of application, especially for the optical, for real application, the uniformity and the uniformity of every cells, the process is very, very important. Otherwise, the noise will be very large.
Yes, yes. That's why we introduced this new methods, use property itself to determine the structure that can provide us a precisely structured fabrication.
Okay, and what about the stability?
Stability, this particle as
the softer one, yeah.
Right. The stability, as you can see, the particle bonding together through the chemical bonding. So the stability should be good.
Mm-hmm. Okay.
I have a follow-up question. So for the same concept that you're describing here, how do you control the density of these particles, avoid clustering events, and how do you maintain the physical properties of this soft metamaterial over time, as potentially there will be Brownian motion, and at the end there will be some clustering events and some sedimentation. So do you need to periodically pulse this system to create uniform density? So how do you handle some of these challenges that relate to the 3D nature of these systems?
That's a very good question. And this answer can be used, this figure, to be answered. As you can see, you're considering about when this metal atom become dense, the coupling between each other will affect the physical properties in 3 dimensions. So as shown in this figure, that this filling factor essentially is the density of this metal atom filling in 3D space. So as you can see, when this filling factor increase, it was still, the physical property will change, but it's still within our controllability of the index as designed.
Okay, Dr. Yang, I have also got a follow-up question. And then your meta atoms are randomly distributed, but ultimately you want to have an arrangement of these meta atoms to be able to have a better control over the actual properties and applications which you want to use it for. Would you like to comment on that, and then how you'll be able to achieve that?
Yeah, so basically the metamaterial essentially consider effective media. So it's not regarding its either it's periodic around them, as long as the meta atom is well below the subwavelengths. So we can consider this bulk material property as an effective medium.
Okay, thank you. I also got a follow-up question on your quantum Casimir force, and then what about the shape of the particles which you're using and what's its impact in terms of your trapping behavior?
That's a very good question. Yeah, geometry will matter in this case. We use a metal plate is just because it's a flat surface and this energy is well defined and is well controlled. If you use a nanoparticle with spherical shape, you will integrate along the surface with different curvature. That will become complicated. Yeah, true. The geometry will matter for this eventual Casimir interaction.
Okay,
thank you
very much.
I also have a question to the Casimir interactions.
Yes.
Very nice talk. Very interesting. So I'm wondering, can you give us a little bit details on how you measure the distance between the nanoplate to the substrate? How can you precisely control that and to measure that? I didn't get that probably.
Okay, yeah, sure. Yeah, that's a very good question. That's a key of the measurements precisely determine the trapping distance. I will use this figure illustrate. As you can see, there's 2 metal plates. This gold is essentially a flat surface of substrate, and this floating one, this trapped gold, is essentially a nanoplate. And between this nanoplate and the flat surface of bottom gold, it will form the fibrin-pearl cavity. So as we know that fibrin-pearl cavity have a well distinct resonance when measure spectrum because of the interference effect. In this sense, we measure this interference dip of this fibrin-pearl cavity, and that interference dip is essentially a function of the trapping distance. We can, from a spectrum, we can precisely determine the trapping distance from that.
Okay, thank you.
Thank you.
Can you comment on the amount of loss that you expect or measure in your first part, especially the magnetic resonance or the negative index?
Oh, okay. Yeah, that's a very good question. The loss is always a problem in the whole field of metamaterials. So as you can see, this magnetic optical mode is a little bit wide. That means the loss is still large.
So because of the limited time that I have, I'll split my talk into two parts. I'll talk about what metasurfaces are and how we use them for some applications, replacing bulk optical elements and what the functionality is enabled by them. And then in the second half of my talk, I'll talk about this integrated platform that I've been alluding to. So a metasurface, as you probably all already know from talks last week, is a compact, ultra-thin planar, CMOS compatible and manufacturable platform for light manipulation. And it is able to provide an arbitrary phase polarization or amplitude modulation to an optical wavefront. So if you just look at very simply from the perspective of a lens, and if I remove the refractive parts of a lens, then what you end up with is this Fresnel lens. And really what metasurfaces are, let's say, from the lensing perspective is an analog of a Fresnel lens, but in a nanoscale platform. Okay, and what really differentiates metasurfaces, I would say, from say a Fresnel lens or refractive optic that could be used to focus light is this ability to give you multifunctional response. And I'll allude to this in my talk and talk about this in more detail. And I really cannot stress this enough, is that this is CMOS compatible and manufacturable platform. So now one can think of creating bulk optical elements in a CMOS foundry in a scalable way. Shown here is a beautiful example from Federico Capasso's group that shows that in a 4-inch wafer, they can make tens or hundreds of these devices. These are all individual lenses composed of these nanopillars that can focus light. So again, this quite elegantly shows this manufacturability or scalability aspect of this approach to shape light. Right? How do they work? So in a very, very simple sense, the building block of one of these metasurfaces is a nanopillar waveguide. And the nanopillar is a high index material sitting on a low index substrate. If I shine light on it, the light acquires a phase shift as it propagates through it. So naturally, if I make the nanopillar thinner, then light will come out faster. If I make the nanopillar thicker, light will come out slower, and anywhere in between. So if I have a library of these nanopillars that can give me 0 to 2 pi phase shift, that's all I need to create, say, a phase shifter. So shown here, this concept is shown here mathematically, where if my diameter of the nanopillar is changed, then I can get the 0 to 2 pi phase shift that I want while maintaining a quite high transmission. Another thing to notice here is that if you keep scaling the dimensions, you will always hit a regime where the transmission goes to 0, akin to a resonance. So these resonances are the local dielectric, geometric, or Mie resonances supported by the nanopillars. And for most part that I will be talking about in this talk, we try to stay away from this resonance, but there are aspects of metasurfaces related to enhanced light matter interactions in, say, nonlinear effects, or to make, say, color filters that can leverage these resonances. But for this purposes, the talk will stay away from this resonance. Okay, so now let's say in a very simple sense, if I want to make a lens, this is the spherical phase functions that is required for the lens. And if I have light incident on this metal surface, then what you basically are doing is this is the phase required. And so what you all you have to do then is to make this metasurface is to map the phase shift to the nanopillar dimensions. So if I want a particular phase shift at this spatial location, then all I do is I pluck a nanopillar and place it here, and I fabricate it. So we fabricate all of these devices here at NEST in our nanofab. I have shown here an example of a metasurface that quite elegantly shows this 0 to 2 pi phase wrap, where this thinner nanopillar gives a smaller phase shift and a thicker nanopillar gives the larger phase shift. Shown here in this optical image are two metasurfaces, 2 millimeters and 3 millimeters in diameter. They look like basically like a pen or a pen mark on a glass slide, but really they are high numerical aperture, 0.9 numerical aperture meta lens. And in this particular case, these nanopillars, these metasurfaces are composed of rectangular nanopillars that is able to focus light at these two wavelengths, 780 and 850 nanometers, at the diffraction limit at a distance of approximately 500 microns. And the reason for these choice of wavelengths was for rubidium trapping application that I'll allude to in a second. Okay, so this kind of quite elegantly shows that in this very, very compact platform, what can enable very, very high numerical apertures and then sort of this multifunctional response. In our group, we work with a number of different materials that are shown in this slide, from silicon, titanium dioxide, hafnia to tantala. ICM images are of the devices that were fabricated here in our group. And really, I want to stress about this material hafnia that enables operation down to deep UV wavelength regime. So if I go to a Thorlabs catalog and try to find an objective that works down to, say, 200, 210 nanometers, it's just impossible to find. And if you are so lucky to find one, it is probably going to cost you $20,000. So really, the metasurface platform based on, say, the hafnia is quite strong in terms of pushing the response down to deep UV. But a lot of other groups have shown that you can do very impressive stuff in the visible frequencies with, say, TiO2 metasurface, and then silicon is of course the workhorse. for operation from, let's say, near IR spectral range all the way up to the terahertz. So it's a quite remarkable material platform choices that are available. I talked about using a nanopillar to control phase to say make a lens or a beam deflector by changing its nanopillar size, but the control is quite broad. One can do amplitude control, one can do phase control and polarization control, and these various capabilities are shown in this slide here, where instead of a square nanopillar, if I use a rectangular nanopillar and I look at the phase shift along those two orthogonal axes and lock it, let's say, to a pi/2 phase angle, then this is basically a nanoscale quarter wave plate. But if you do the Jones matrix, what you find out is that not only does it change a linearly polarized light to say a circularly polarized light, but it also gives us a phase shift. Similarly, one could take a nanopillar and impose a condition of a pi phase shift or a half wave plate. And if I make a polarizer on the back, then a half wave plate with a polarizer is an amplitude modulator. So again, in this very, very compact platform, one can modulate amplitude and phase simultaneously. And these are sort of propagation phase-based approaches, but there's another approach which is referred to as geometric phase or PB phase, where again, you design the nanopillar to act as a half-wave plate, but instead of shining linearly polarized light, if you shine circularly polarized light, and what you get out is an opposite-handedness light with a phase shift given by the rotation of the nanopillar, not by its size. And so in terms of fabrication, this is more forgiving because you're only trying to make a nanopillar of the same size and rotating them by different amounts. And whereas here you have to make nanopillars that are of different sizes. But really what this shows is this very, very simple approach of using very simple geometries to control phase, polarization, or amplitude of light going through it at the nanoscale. And so I've kind of alluded to some of the applications in the field of optics, but this field has quite exploded in the last few years, where I just cannot simply do justice to putting all the applications on this slide, but it has enabled a lot of very, very unique aspects in the field of optics. But there has been a lot of work done in this area of what I call inverse design or topology optimization that my group also works in, where it's an output first approach. So you tell the program what output you want, and then the program spits out the design that looks quite intuitive as shown in this slide here, but it does this function in a very, very, very high efficient way. So shown here is an example of a 1 micron light that is deflected to 75 degrees with almost 99% efficiency using this. So it is basically a diffraction grating, at least in this slide, but it does it at a very, very good job. There has been work done in the nonlinear aspect where people have used metasurfaces to shape light, the nonlinear beam rather than the linear beam, for high harmonic generation and various other applications. And more recently, there has been a lot of quantum aspects of it, from generation of single photons to entangled photon pairs, an array of entangled photon pairs as shown in this elegant paper that came out this year, to sort of doing polarization state tomography of end polarization input state of photons. So there's a huge range of applications where these have been applied, and we study some of these aspects in our group, but for the purposes of this talk, I'm going to be talking about using metasurfaces for, say, atom trapping. And this sort of came from a collaboration that we are currently underway with Cindy Riegel's group at Gila Boulder, where we are looking at metasurfaces as a potential tool in an atom physics lab. And really, the considerations are that the requirements in an atom trapping lab or atomic physics lab are quite different from, say, a free space lab that I have, for example, or one of you guys have. And so how does one handle and operate such a device in an UHV setting in an atom trapping lab is a consideration. And also, these metasurfaces are not ideal. They lead to non-ideal light profiles or scattered light at the location of the atom. So some of those things have to be considered. So before one jumps the gun on trying to use these, one has to consider all these aspects before using them. So what we decided was a simple experiment where we said, okay, why don't we try to make a mod out of a metasurface as in a lattice configuration. So shown is here is a picture of a rubidium mod that was brought to the location of the in this sort of center of this red arrows, and then this rubidium mod was put in this lattice configuration using this retro-reflected beam, and one of the lenses in this retro was replaced by a meta lens shown here, and indeed what they showed was that we are able to trap an ensemble of atoms in a 130 microkelvin deep lattice. One can look at now these trapped atoms quite carefully, their lifetimes or looking at the atom number as a function of modulation frequencies and compare them to conventional optics. And basically what this slide is showing is that meta lenses are really not doing anything untowards towards the atom, and they are basically behaving very similar to how one would expect a conventional optical element to behave. So this was quite promising, and where this is really going is trying to use meta surfaces to trap single neutral atoms, and these single neutral atoms act as qubits and are a very attractive candidate for quantum computing applications. So shown here is again the setup where we bring a two-dimensional rubidium mott close to the metasurface focus, and in this particular case, instead of a low NA metasurface, this is a tweezer trap. So it's a high NA metasurface that is actually mounted inside the science cell. In this case, this particular metasurface is a 0.9 numerical aperture meta lens. And here you can see the mott close to the metasurface, and here is the lower NA metasurface 0.55 that with the mott slightly further away from it. And basically the status of these experiments currently is that we are looking for single atoms to be trapped, and we are quite hopeful that in the next few months we'll see them. But basically the goal is to try to use such a scalable manufacturable platform to trap single or an array of neutral atoms to both enable new physics such as entanglement and other effects that one could study with these trapped atoms, but also scale them such that they are one can make these platforms for quantum computing applications. Okay, so in the second half of my talk, I'll quickly go through this effort on using metasurfaces for together with integrated photonics for quantum systems. And so this slide probably needs no introduction. There's been a number of talks on the power of this integrated photonic approach, where now one can design a complete set of optical experiment on chip using, say, a photonic foundry platform, where both the lasers, splitters, interferometers, and detectors can all be basically on a chip in a very compact platform, as shown in some of the slides by some of the speakers earlier today. A number of companies are working on it from a datacom perspective to LIDAR and whatnot, a number of applications. You can use a number of softwares. So this is a fantastic platform because I think now photonics, one can say, has reached the maturity level of, say, microelectronic industries. But there's one problem with PICs, and the problem with PIC is basically that light always stays confined in this two-dimensional volume, and always confined to these waveguides. And so, but there are a number of applications that a lot of us work on, say in talking with biological systems or AMO systems, or even trying to trap or cool macroscopic objects in free space. And in all of these systems, light matter interaction is necessarily required in volume rather than at surfaces. So PICs are great in terms of keeping light within a waveguide in the sub-micron dimensions, but there are a number of applications that require beams to be centimeters or millimeters in sizes with very well-controlled directionality, divergence, and polarization. And so how does one use the best of both worlds, which is things that free space optics gives us, but also the manufacturability aspect of, say, integrated photonics. And this was addressed in a series of papers that came out together with Vladimir Aksiu's group here at NIST with a collaboration, where basically they showed this extreme mode converter platform, which is, if I have light in a waveguide and I want to come out of the chip with a decent beam diameter, then what you do is you do this one-dimensional light leakage into the slab mode of the waveguide. So now you have adiabatically expanded this beam in one dimensions, and then now if you hit an apatized grating and you look at the beam coming out, then really what you have is a beam that is hundreds of microns in diameter, going from hundreds of nanometers in diameter, with a very well-controlled polarization, in this case linear, and a very well-controlled directionality given by the pitch of the grating. But what really enables the functionality is the metasurface aspect, where we showed that if we make a metasurface directly on the second layer lithography, or we bond a metasurface chip directly to the top of this extreme mode converter, then now you can leverage all the capabilities of a metasurface, such as changing phase, polarization, directionality, divergence, and whatnot that metasurface enables one to do. And the reason we were developing this compact platform of taking guiding light on chip on waveguides and then using metasurfaces to give us these beams is for portable atomic clock applications, for a program that is currently underway here at NIST together with a number of collaborators. And basically what this is showing is that if you look at one of the best atomic clocks in the world, this is how the lab looks like. If you've been to an atomic physics lab, then this is how they look like. They're quite complicated. And to leverage all these capabilities that atomic clocks gives us, really one wants these clocks to be portable and manufacturable and at least movable. And an effort was done at Europe in trying to make a strontium atomic clock on a tractor trailer, where they drove this tractor trailer around Europe to do geodesy, sort of mapping the topography of the Earth, if you would. and for navigation applications. So they were using these, but really the idea is to use this platform of PIC plus metasurfaces or these functionalities of manufacturability to create an atomic clock in a very, very compact platform. And naturally, this is not everything. There's lasers that are outside this package. But for the purposes of this talk, I'll like to only focus on this area, which is called the physics package, which is where light is and how it is guided and used to trap atoms. And so if I look at this physics package, what you are seeing is a PIC plate, which is the photonic integrated circuit shown here with these lines and these dots, which is where you have light that will come out of the PIC using this XT mode converter. And then these Lego blocks is the metasurface plate that will give us the divergence, directionality, and dimensionality that is needed, and along with well-controlled polarization to trap atoms. So what you really notice here is that if I am trying to trap strontium atoms using in this hybrid cubic mod geometry that is shown here, that we came up with after a lot of calculations, then you have a number of wavelengths that you're working with for strontium atoms. You need beams that are almost a centimeter in size, at least for the blue mod beams. You need very specific polarization and you need very specific directionality. So if one of these things go bad, then you will not see atoms trapped, right? So how are we doing this? We are doing this in a two-step manner. In the first step, we design a photonic integrated circuit based on silicon nitride platform operating at this 461 nanometer. And you use this PIC platform to guide light and outcouple from these extreme mode converters. And if I zoom in one of these extreme mode converters, then what you see is indeed one can get these beautiful Gaussian beams out of it. If I look at this movie, then what you see is that indeed this PIC platform with 6 emitters in this case can direct light to specific angles. But what you notice that these beams are still linearly polarized and only hundreds of microns in diameter. Whereas what you need really, at least from this slide, you can see is that we need beams that are almost a centimeter in diameter that are also circularly polarized. So that magic is done using metasurfaces. So I won't go through all the metasurface requirements in this project, but basically if I take one of these Lego blocks, let's say this blue one, and I look at it closely, then what this blue block metasurface is required to do is to take the linearly polarized 100 micron beam from the PIC and convert it to a circularly polarized light, diverge it with quite high NA, and also change its directionality. So really this one Lego block is doing the job of 3 free space optics, is doing the job of a mirror, is doing the job of a lens, and it's doing the job of a quarter wave plate at these 2 wavelengths. So it's quite remarkable, this multifunctional approach. So indeed you can make these, design this, and fabricate these. So shown here is the PIC plate. So if you look at this drawing in the center, what you notice, these dot marks are hundreds of microns in diameter, and these are the metasurfaces, these Lego blocks, and they can do the function that I just talked about. So if I shine light on one of these dot marks on these in this plate, then and you look at the beam in the far field, then what you see is that these diverging beams coming out, these are circularly polarized beams, or these beams that are sent at 45-degree angles, also with circular polarization. So the idea is basically that now this particular meta plate, if you would, is going to be flip chip bonded to the PIC plate, and then it will give us these beams that we want while still using fiber coupled and PIC platform to guide and route light. And then of course there's also the reflector plate that is going to deflect light, and to trap atoms. So this is currently the status of this project. Another quick example, this is my last slide that shows that if I have a PIC, then I can use this PIC plus metasurface approach to trap atoms in a completely planar configuration. So this work was spearheaded by William McGehee when he was here at NIST, where he showed quite elegantly that if I put these things together, then and use this gating mod approach, then one can trap atoms with performance that is better than say one would get from a Gaussian beam, because of the ability of metasurfaces to create circularly polarized flat top beams. And in this particular experiment, we chose a 6-inch distance between the metasurface and grating. But there's no reason why we cannot choose, say, a higher numerical aperture for the meta lens and bring it closer and really shrink the size down. So again, this kind of alludes to this manufacturability and compactness aspect, where using the capabilities of metasurfaces in a very compact platform, we can give it the multifunctional approach and really make them manufacturable. So I think with that, I think I'm out of time. So I hope I have shown you in this talk is a very elegant manufacturable PIC platform based on metasurfaces for atom trapping and atomic clock applications. I've only talked about this, but however, there are opportunities in a number of different areas. People have shown very cool results in LIDAR to imaging. Our group works in the field of ultrafast optics, in pulse shaping, which I didn't have time to get into at all, shown in this paper that came out last year, to quantum optics applications. So the application range is quite broad. And so with that, I thank you for your attention, and I'll be happy to answer any questions you might have.
Okay. Thank you, Amit, for your talk.
I have a quick question. Very nice talk. Regarding the meta surface plates that you've shown to couple into free space modes, what is a typical coupling efficiency, energy efficiency that you're getting with these types of surfaces for free space mode?
So the efficiency for, let's say, a meta surface that looks like this, a multifunctional one, is in the order of 70 to 80%, which is typical for all meta surfaces that we work with. Even the reflector that is shown here, we are getting efficiencies around 70 to 80%. So, but what is I guess more important is that this is the beam power that we need at the atom location. Otherwise, we won't see atoms, right? And if we use decently enough powerful laser beams, then this 60 to 80% efficiency numbers are acceptable. But maybe for some applications it may not be, right? At least for this program, it is quite acceptable.
Amit, I have a question. And so the very nice talk. And when I was looking at some of your structures, there seem to be a lot of non-uniformities on the surface, like, those pillars are not looking very uniform, and there seem to be a lot of surface roughness. And then would you like to comment on what is the influence of that in terms of performance of these meta surfaces?
The reason you see surface roughness is because these are high index dielectric pillars on a low index substrate, silicon dioxide. So we coat them with aluminum or E-spacer to take SEM images. And so it's really a issue of taking scanning electron microscopy images. And so, but the underlying pillars themselves are quite clean. And so I apologize, I didn't make that clear.
Oh, okay, that's good. Thank you very much.
Mostly to take SEM images, we put a conductive layer on top.
Okay.
So that kind of makes it look like that, right?
Okay. Can I ask a question about your atom trapping? And with all these meta surfaces, will you be able to create a two-dimensional array of atom traps? So what are the challenges you think you'll be able to, in terms of achieving that?
So usually, currently, if you look at is by using a lower numerical aperture lens with a very large field of view. And what they do is they modulate the beam using an acousto-optic modulator, both in X and Y direction, quite fast. And if you do it fast enough, then atom doesn't have time to leave the trap, right? So there's a lifetime to the atom shown here, let's say seconds, right? And I can modulate my AOM at megahertz speed, right? So you can basically deflect the light quite fast and then basically create an array of these traps where the atom doesn't have time to leave, right? And so the challenges for metasurface with this high numerical aperture optics, at least, would be how does one increase the field of view, if you would, of your metasurface. These are singlets, right? So the field of view, at least at this high numerical apertures, are quite limited. But if one goes to, say, a doublet approach, then maybe to say plus minus 25 degrees. But at least in this experiment that I showed you, we are really looking at trying to trap single atom just to see if we can even trap a single atom or not, right? But the challenge really would be to increase the field of view of these metasurfaces based lens.
Okay, thank you.
I have a question, and it's very interesting talk and a good job. And what about your capability for your beautiful picture for different pillars? How large can you make for your? Maybe we can see it's an optical element. Yeah.
Okay, so so we use electron beam lithography. So electron beam lithography, we are basically limited by the write time.
Yes.
So the largest, let's say, we are making for this program is a chip that is shown here. This blue dot is approximately a centimeter size. So we are trying to make a metasurface. There are 3 1 centimeter size metasurfaces and 3 smaller metasurfaces. Writing these metasurfaces will take approximately, I would say, I don't know, a whole weekend. But there are faster e-beam write machines that are 100 megahertz, and you can probably cut that time down to 24 hours. But it is a serial process. So the challenge is really trying to come up with an approach where maybe instead of e-beam, they can be fabricated using deep UV stepper lithography, right? And so stepper is right at the limit of where they can give you certain functionalities, but if all of these devices can be made using deep UV, then that's the way to go. E-beam is great, but it is a serial process at the end, right? So, but we can make centimeter scale metasurfaces as overnight writing or say a writing over time over like 10 to 12 hours.
Okay. Thank you.
I have a question. Very nice talk about your focusing property of your metal lens. You have one slide somewhere talking about you reached 0.7
numerical aperture.
Yeah.
This one.
Yes, exactly. So I'm wondering if it's possible for you to achieve, because for metamaterials, sometimes you can achieve superlensing effects.
Right.
Of course, for metal lens, you are trying to replace the normal lens to a flat lens. So if it's possible to combine these two effects together to have a sub-wavelength focusing effects with a flat metal lens.
That's a good question. I think these are still diffraction limited approaches, at least because they are still using diffractive optics. To get super resolution, I would say one really has to use these meta lenses or meta surfaces in a super lensing condition, if you would, like techniques such as STED or STORM or PALM. I just don't see how one can use a meta surface that is purely diffractive to get to sub-wavelength resolution. Unfortunately, I don't have a good idea for it. No one would do it. But I see what your question is, and I don't have a good answer for it. I apologize.
Anyway, it would be interesting.
Right. Definitely, yeah.
Amit, great talk and great work. I had a question about frequency dispersion of the response of these meta lenses, and if you are pursuing any approach to try to address that. So
our work is mostly currently focused on atom trapping, and the fantastic thing about atom trapping is you are always working with discrete wavelengths, right?
Yes.
So we can get away with designing meta surfaces that are very that do the job well, and they do the job well at this one wavelength, or maybe at two wavelengths at best. Let's say 780 and 850 for rubidium. But there are other groups that are working on sort of the achromatic aspects, as shown in this slide here, Federico Capasso's group, Nanfang, and whatnot. And really what you need to go to an achromatic or increase the dispersion is more degrees of freedom. We work with 1 nanopillar. If I fix the height, then the only degree of freedom I have is its width, the two different side lengths. But if you go to say a 2 nanopillar or a 3 nanopillar, then what you have really done is increase the degrees of freedom from 2 to, let's say, 10, and then it's a data mining approach or try to get the GVD to be 0, right? So at least for the applications we have in mind, we don't need achromatic performance, but there are efforts underway in the community in trying to give the achromatic performance using a more complex metasurface unit cell designs.
Okay, great. The time is right up. So Amit, thank you again for your talk.
Thank you, Renmin. I appreciate it.
Thank you. So let's move to our next candidates. Dr. Yi Yang from MIT. Hi.
Hello, everyone. Okay, so should I start now?
Yeah, okay. Can you share your slides?
Yeah, sure.
Okay, so Dr. Yang will talk about exotic electromagnetic scattering, near field, far field, and the synthetic phenomena. Please, E, time is yours.
Okay, thanks. All right, let me first switch to a pointer. All right, so everyone can see the pointer now?
Yes.
Okay, good. Okay, so good morning, afternoon, and evening, everyone. I'm Yi Yang from the Marin Soldier group at MIT. I was a grad student of Marin and now a postdoc in the same group. And today it's a pleasure for me to share some of our results on electromagnetic scattering. And I'll tackle this topic from three perspectives: far field, near field, and the synthetic perspectives. So before I start, I would like to thank our MIT team, my advisor, Marion, John, Stephen, Carl, as well as my colleagues at MIT, our alumni, Bo, Ido, and our...
Ian, you're cutting off a bit. Can you see whether you can, some signal problem is there?
Oh, so it's not very clearly?
Yeah.
Okay, so let me maybe make it, let me increase my voice. Is the voice problem or it's a signal?
It's more of a little bit of breaking up.
If you want, use a cable like a headset that is hardwired, that might help you.
Okay, so let me do that. Okay. So does this look better? Can be heard better?
Right.
Okay, good. So I'll continue. So I also thank our external collaborator, Chao, Hovoy, and Wei. All right. So today I'm going to talk about a simple concept, is electromagnetic scattering. So this thing is a concept can be understood this way. So you have some optical environment, and you can define an obstacle in this optical environment. So when you apply excitation to this optical environment, you cause extra polarization inside the scatter, whose re-radiation can be understood as a scattering. So the first part of my talk deal with the far field scattering experiment that enable us to introduce a nanoscale electromagnetic framework. So if you think about classical electromagnetism, there's this peculiarity that you have this, once you specify the geometry as well as the bulk constitution material, you can almost solve for everything. And if you live in this non-retarded regime, the solution is even scale invariant. So where are this intrinsic electronic length scale that's supposed to play some role here? In fact, people are aware of this, and there have been different experiments with either optical or electrical excitations that probe these effects, and they observe frequency shifts and broadenings, as well as the reduced field confinement in the near field. So there are also a series tries to tackle this problem, but they always face a dilemma between rigor and computational scalability. I don't have time today to cover those theories, but I would like to argue today that this Feibleman D parameters introduced by Feibleman will serve a nice solution to these non-classical effects for length scale larger than 1 nanometers in nanophotonic platforms. So this D parameter is defined for interface comprised of the material A and B, as well as it has two components, the perpendicular term and the parallel term. So let me explain what this D parameter is. So let's think about this simple metal ionic interface for metal on the left, and vacuum is on the right. So you have this equilibrium charge density that's gradually written down from this metal into the vacuum as calculated from quantum mechanics. But in classical mechanics, this equilibrium charge density is assumed to be a step function rather than a smooth written down function. So as a result, under optical excitation, the induced charge density is given by this sharp delta function that locates exactly at this ionic interface. But quantum mechanically, this induced charge density does not do so. Instead, they have a non-zero spatial extent near this ionic interface, but deviate from the exact interface. So the exact deviation from this induced polarization away from the ionic interface is defined as the Feibleman D parameter, the perpendicular term. Okay, and analogously, you can define something similar for the parallel term of the D parameter, which is the centroid of the derivative of the surface current. So if you think about this electromagnetic response, we can understand the classical response as a monopole approximation of the induced polarization, while we can treat this d parameter terms as the dipolar excitations. So since they are dipolar excitations, they effectively drive surface dipoles and surface currents that's proportional to the surface field discontinuities. And you can recast those extra source terms into Maxwell's equations by transforming the classical boundary conditions into a set of mesoscopic boundary conditions. And you can see that in the limit that d parameter becomes 0, the mesoscopic boundary conditions reduce to the classical boundary conditions. And we implement those boundary conditions in an openly available commercial solver. And I encourage you to take a look at the solver if you have a need. So I emphasize that these boundary conditions is general because they remain agnostic about the specific optical problems. So to experimentally test this framework, we choose a quintessential gap plasmon nanoresonator comprised of a gold nanodiscs and a gold substrate. So in between them, there's this aluminum oxide thin layer that's defined by atomic layer deposition. So it is known that these structures support well-confined gap plasmon underneath the nanoresonators. And our non-classical calculation shows that the non-classical dipole density is also pronounced underneath the nanodiscs. So this calculation indicates that we may be able to observe a pronounced non-classical effects in this setup. So indeed, that's what we see. We build a tabletop dark field microscope with tunable magnification, and we probe the fundamental dipolar resonance of the structure. We find that there is as large as 300 nanometers of the frequency shift for the smallest gap around 1 nanometers. So this enables us, give us a chance to do an symmetry for a surface. So this analog is doing as follows. So we can do a bulk response characterization by measuring the real part and imaginary part of a bulk material using ellipsometry. So what we want to do here is to do a surface ellipsometry by measuring the real part and imaginary part of the d parameter as a function of frequency. So this characterizes the surface response of two materials that comprise of an interface. So here's what we do. So we do a two-dimensional sweep measurement. So we vary the gap size, which is indicated by color. And we also change the diameter of the nanodisk, which is shown by columns. And we track the real part and the imaginary part of the complex resonant frequency as shown on the right. So for the real part of the complex resonant frequency, we find that there's a consistent blue shift of the resonance as consistent with previous measurement on gold. So for the imaginary part of the complex resonant frequency, we find that there's a general broadening. But a key feature in here is that the smallest gap size does not give us the largest broadening. So in this indicate that the surface response of this interface could be strongly dispersive. So to the last piece to connect this, to complete this picture is to use the quasi-normal perturbation theory, which connects our measured frequency shift, omega-1, with the mesoscopic d parameters via a set of perturbation strengths kappa. So this kappa has a clear physical meaning that they correspond to the classical energy difference across a given interface. So we calculate these perturbation strengths for different structures, and we find that the perturbation strengths of our experimental choice is much larger than those of other widely used platforms. So this justifies that why we were able to see such pronounced non-classical shift in our measurements. So we're able to measure these d parameters, extract those real part and imaginary part of the d parameters, and to obtain their dispersion. So we see that the real part of the d parameter is dispersionless, while the imaginary part of the d parameter is strongly dispersive. So this strong dispersion actually corresponds to the reason why we see the breakdown of the cryobic light broadening at the smallest gap of our structure, where the broadening is not the maximum. So this measurement is particularly meaningful because the theoretical calculation of the D parameter for noble metals is very challenging. So the second part of my talk deals with the near field treatment of free electron radiation, which enable us to obtain an upper limit to its spontaneous emission and energy loss. So we frame this free electron radiation in the following scattering scenario, where we have electron passing by a structure in the near field with a separation D, and the structure is defined by the volume and the optical susceptibility. And this process will generate radiation and absorption. Taken together, they're known as extinction or energy loss that can be probed by electron spectroscopy. So I'll skip the math here, but I will directly show you the result. So what we obtain here is the emission probability per unit frequency must be smaller than this quantity, which has some physical constants, a material factor in blue, and the structure factor shown in green. Okay. And we test this upper limit by numerical simulations on different structures. For example, here is the bow tie antenna with optical emission, and here is the grating that emits radiation in the deep ultraviolet. So we test our upper limit theory by measuring the Smith per cell radiation. So Smith per cell radiation is a process where free electron pass through a periodic structure at a glazing angle and generate radiation due to momentum conservation. So we test our upper limit theory by measuring the free electron radiation from a one-dimensional grating made of silicon and gold at different free electron energy. And what's interesting here is that we find that the envelope of those measured emission spectrum has a peak envelope, and it is captured by our upper limit theory. So the reason for this peak envelope is has two reasons. So towards the long wavelengths, the reduced brightness of the electron gun will increase the electron structure separation and thus reduce the emission probability. But towards the short wavelengths, it is the material response of both silicon and gold that reduce simultaneously, which accounts for this reduction towards the short wavelengths. So we do a complementary measurement in the near infrared. I use a different structure with longer period. And with this time, we see that the emission probability has a nearly monotonic reduction towards the long wavelength. So this time, the material response is much more flatter in this spectral window compared to that in the optical regime, but the reduction of the brightness of the electron gun still persists, which accounts for this reduction of the emission probability. So aside from these experimental verifications, there are also a few predictions that's pending experimental confirmation from our upper limit. So the first one is a regime where slow electron can radiate more strongly than fast electrons. So if you look, we obtain the upper limit, specific upper limit for the Smith per cell radiation, which is highlighted by this G function, which has two arguments: the electron velocity normalized by speed of light beta, and as well as this dimensionless impact parameter KD, indicate the separation of electrons compared to wavelengths. So we see this G function looks like this, okay? So it's highlighted by this bright belt. So if you're in the far field where KD is large, relativistic electrons is optimum to generate stronger radiation. But as your separation gets smaller and smaller, slow electron gets favored. So this regime is quite interesting, and it's quite counterintuitive too. So in fact, this characteristic is not limited to Smith per cell radiation. If we go back to the shape-independent upper limit, and we find that this dichotomy of the radiation regimes still there. The reason of this dichotomy is because mathematically of this different asymptotic limit of our upper limit towards either near field or far field. So a second prediction is that there is an apparent divergence of our upper limit in the limit of lossless dielectric material. And we show that this is not a pure mathematical peculiarity. Rather, you can realize this situation by coupling free electrons with optical bounces in the continuum, which gives you a enhancement via the infinite quality factor as well as the coupling, outcoupling capability. And we do a numerical simulation to confirm this prediction by varying the electron velocity. And we show that there is indeed a divergent emission probability near these BIC resonances. So taken together, both predictions 1 and 2, we show that it is possible that to realize efficient nanophotonic sources that's based on non-relativistic electrons. So the last part of my talk deals with synthetic gauge fields. So it's a synthetic scattering phenomenon where photons scatter with magnetic fluxes. So it is quite well known that the AB effect tells us that you can imprint a geometric phase onto a charged particle by threading in magnetic fields that's surrounded by the path of the charged particle. And if you place this geometric phase into a lattice, you can obtain quantum Hall effects that correspond to this famous offset butterfly. And for photons, things can be tricky because photons don't carry charge. But in the seminal work from Shenhui's group, they realized that you can, in fact, have effective magnetic fields for photons by implementing dynamic modulations to break time reversal symmetry. And later, this proposal was realized in both in the optical regime, in the microwave regime, and in the integrated photonics. So it would be natural to consider whether we can realize the non-abelian gauge fields for photons. So to realize this goal, there are two prerequisites. The first one is we need an internal degree of freedom, either spin or pseudospin. And the second requirement is a path integral loop operators that's highlighted by these inhomogeneous gauge fields. And the simplest situation to realize this non-abelian gauge field is the non-abelian Aharonov-Bohm effect, as shown in here. So you have a point in space, you have a spinful particle, and the spinful particle undergoes a reversely ordered path integrals, either from the top or from the bottom. And these two constitute of inhomogeneous gauge fields that's indicated by sigma y and sigma z, which are Pauli matrices. And the interference of the two resulting pseudospins, either from the upper pass or the lower pass, is known as this non-abelian AB effect. In fact, this effect has been discussed in different contexts, from higher energy physics, cold atoms, and more recently in photonics. So in Hilbert space, you can understand this this situation as follows. The gauge fields serve as a rotation along certain axes of the Bloch sphere. But if you have non-abelian gauge field, the rotation is along different axes. And we need to differentiate those non-abelian gauge fields versus single cubic gate because they correspond to the difference between non-abelian gauge fields and the single cubic gate is that non-abelian gauge field couples to momentum, and therefore they contain a sign flip upon reversal of the propagation directions. So we realize this non-abelian gauge fields by breaking time reversal symmetry in different bases. So the first one is the Faraday rotation, as is well known, and the second one is the dynamic modulation using lithium nanobe modulators. And we do this by modulating 4 lithium nanobe with sawtooth modulation and V2 pi, which give us an effective sigma z degree of freedom for the non-abelian gauge field. And in the full setup, we combine the two we combine the two ends of the point A and B into an interferometer, and we read out their interference by doing a projection detection. So the observable of our AB effect is defined as the contrast between the up pseudospin and the down pseudospin that's defined on this S2T2 manifold has 4 parameters that we can tune. And we can show this interference contrast function rho corresponds to this interference contrast on the Bloch sphere that's highlighted by a set of tunable poles and zeros. And we're interested in the tunable poles and zeros as a function of the non-Billiard gauge fields theta and phi. So here's our results that we are able to tune the instant pseudospin alpha and beta on the Bloch sphere, and we fix our gauge field choice on the synthetic torus. And we managed to show that our synthetic gauge fields can either in the abelian regime where our poles and zeros all live on the equator of the sphere, or if we are in the non-abelian regime, that the interference poles and zeros appear away from the equator. So this is a key feature that differentiates our non-abelian gauge fields. So we're also trying to leverage those non-abelian gauge fields with larger systems such lattice, and this is ongoing work. So in the end, I show you a few electromagnetic scattering problems, a far field experiment for a nanoscale framework, a near field radiation upper limit, as well as the synthetic non-abelian AB effect. So I hope that some of them could be interesting for you, and I'd like to thank you very much for your attention.
Thank you, Dr. Yang, for your talk.
Yeah, thanks.
Okay, so the talk is now open to questions from our judges.
I have a question regarding your the first part of your talk. Very nice presentation. Thank you.
Thanks.
In the first part, when you talked about the D parameter analysis, maybe I missed it. Are you considering surface roughness as part of your analysis?
Oh, thanks for the question. Indeed, we do model the surface roughness in our structure. And the key to our analysis is that because in our fabrication, okay, so in our fabrication, there's a crucial step, which is this atomic layer deposition and aluminum oxide. So this process is conformal. So whatever surface roughness in the first step is inherited in this layer deposition, and also inherited with latter processes. So the surface roughness will be conformal underneath this nanodisk resonator as well as the gold substrate. So our numerical simulation that under this conformal condition, that this surface roughness will have a more negligible contribution compared to the change of the gap size is given on our experimental conditions.
Thank you for the nice talk. Would you like to, sorry, Andrea, you want to go? Please go ahead.
No, go ahead. Sorry.
Would you like to, I can see that picture in RCM. It's not a very symmetrical shape. It looks like a lot of non-uniformity in terms of getting that circular shape which you're showing in the schematic. And what's the impact of that in terms of the performance of these resonators? And also, what are the losses resonators with using metals?
Oh, thanks. So I'll first answer the first question. Yeah, so yeah, you can see here, indeed, this nanodisk resonator is not a perfect sphere. And in our experimental measurement, we adopt a depolarized excitation. So therefore, we effectively excite an average dipole moment along an arbitrary orientation along this nanodisk. So this is the reason why actually we choose to work with a nanodisk rather than other structures, because it's less sensitive to the polarization change. And since we use depolarized light, the averaged diameter of the nanodisk serve as a nice parameterization of this overall effect. And second question is regarding the radiation efficiency, right? So how lossy these nanoresonators could be. And I can tell you that the efficiency of this resonator is radiation efficiency is quite low because the plasma is extremely confined within the gap, which is a few nanometers. So the efficiency we obtain is like around 1% or even smaller. So this is actually the reason why we need to resort to a cluster measurement rather than single particle spectroscopy. So I know that if we replace this nanodisk with spheres, this will increase the outcoupling efficiency significantly. And this is the reason why, for example, seminal works by Baumberg group and other groups, and they adopt this nanospheres rather than nanodisks because of the high efficiency. But in those structures, as I show in here, that their non-classical correction is much smaller in the structure. So it's a kind of a trade-off thing, but because our work focused on quantifying these non-classical corrections, we choose to work with low efficiency structures. Hope that this can address the question.
Good. Thank you very much.
Yeah, thanks.
Thank you for the great talk. I wanted to ask a question about your enhancement of radiation at the bound state. And I wanted to know how do you expect this to compare to working actually near a Van Hove singularity? And why?
Repeat, compared to what process?
To working near a Van Hove singularity. So
Van Hove singularity.
Yes. So when actually the dispersion becomes flat, because I would expect that more than having a very low imaginary part of the wave number, actually concentrated density of states would actually be more beneficial.
Oh yeah, thanks for the question. And in fact, this is something we're also considering. Because this thing is because in our system here, as you know here, our probability is defined as d squared gamma over dx dy, meaning that it's a two-dimensional system. So once we consider three-dimensional system, we need to remove homogeneity towards one dimension. We need to consider leveraging this Van Hove singularity to combine both this extreme high cube and also the flat band flat band contribution. So taken together, both of these contributions, in reality, we're going to eventually realize this thing. And in fact, we'll have exactly have an ongoing work that leveraging both these effects and the Van Hove singularity that you mentioned. Yeah, that's very sharp. Thanks.
Thank you.
Okay, we have a few minutes more for questions. Any questions from our judges? I got a question. So for the free electron spontaneous emission experiment, can you explain how do you measure the absolute power? Because you show a upper limit for the radiation depending on the frequency. So how do you measure the absolute power of the radiation?
Oh yeah, thanks. So this is something based on a calibration process that I didn't have time to show today. So basically, what we do is to have a optical source that's placed exactly at this setup to replace the electron beam radiation. Okay, so this optical source has a well-documented optical source information, and therefore we use this calibration measurement to compensate all the optical loss in the whole process. So we compare this measurement versus the calibration measurement, so we can obtain the absolute emission probability.
Okay, so you already consider the spatial distribution of the radiation?
Oh yeah. So that the optical source is a calibration source, which has a detailed spectral distribution of the source.
Okay,
So
thank you.
Yeah, thanks for the question.
Okay, so we may have 1 minute for one quick question. Any quick question from our judges? If no, let's thank Dr. Yang again. Thank you for your nice talk. Okay,
thanks everyone.
Okay, thank you. Okay, let's move to the last talk of tonight, which will be given by Dr. Julia Taliabu. Hi, Julia. Are you ready?
Hi, everyone. Yes, I'm gonna share my screen.
Okay.
Can you see my slides right now?
Okay, now we can see it.
Okay, great. Perfect.
Okay, time is yours.
Thank you very much. And it's a real pleasure to be here today. My name is Giulia Tagliabue, and I'm an assistant professor in mechanical engineering at EPFL. And now I will be shifting a little bit gear compared to the previous talks, and I will be talking about the use of nanophotonic structures for energy applications. And in particular, we'll be talking to you about the work that I've done in the past few years related to the use of plasmonic structures for solar fuels. So let me first give you a few words on what solar fuels are, and in particular, what type of solar fuels I'm thinking about. So solar fuels are entail the possibility of generating, in this case, carbon-based fuels, which could be, for example, ethanol, from an electrochemical process that recombines water and carbon dioxide together. So this is obviously very interesting because it creates a carbon neutral cycle that will be very beneficial for climate change issues. And at the same time, it would allow us not to change our energy structure, meaning that we could continue using high energy density liquid fuels, which are already compatible with all the technologies that we are used to. So the idea here is that to power this electrochemical conversion process that requires a lot of energy input, we are going to be using light, and in particular sunlight. So there are obviously two phases to this problem. One is the electrochemical aspects, and the other one is the photonic aspect. What is interesting here is that this process is quite complex, and it typically suffers from a poor selectivity. What I mean here is that this is not just a single chemical reaction, but in reality is a plethora of competing chemical reactions with very similar thermodynamic potential. And therefore, whenever we drive this process, we end up having a mixture of both liquid and gaseous products that then would require a lot of energy to be separated. So the major challenge in this field right now is how to drive this reaction in a selective manner, producing only the fuels or the products that we are interested in. So what is interesting from the photonics and nanophotonics point of view is that for the electrochemical aspect, metals such as gold and copper have emerged as excellent electrocatalysts for this reaction. In particular, copper is the only metal that currently is able to generate products with carbon-carbon bond, such as ethanol. At the same time, we all know that metals such as gold and copper are plasmonic metals. This means that under illumination, they support a collective oscillation of the electron cloud that we call plasma resonance. And we know very well how we can manipulate the optical properties of this nanostructure by generating highly absorbing systems with tunable optical properties. So the question that arises is whether we can use plasmonic nanostructures to both enhance CO2 reduction, but also, and most importantly, to improve the selectivity of this process by directly generating the charges in a metal which is a catalyst. So the question here now is how are we thinking of generating electrical charges in a metal? In fact, typically we use semiconductor to make photoelectrodes. The thing is that we have to go back and analyze the processes that occur in a metal during and following photon absorption. In fact, typically we used to think of metal as purely lossy materials where all of the energy of the photon is dissipated into heat. However, when we look at this process on a time scale, there are actually two intermediate steps which are quite interesting. In fact, from the dephasing of the plasmon and the photon absorption, quite promptly we can generate an electron hole pair, and it's only on a hundreds of femtoseconds time scale, then these carriers will collide with each other and thermalize. If we have a look at the energy distribution of these electrons and holes in the band structure, things become quite interesting. So what you're seeing in these bottom graphs is indeed the Fermi-Dirac distribution of the electron population in the metal. Obviously, when we start, we will have that this Fermi-Dirac distribution has a temperature and that is equal to the lattice temperature and the temperature of the environment. However, upon prompt generation of this hot electron and hole, we would observe a population of electrons and holes which have a very strange distribution, which cannot be described with a specific temperature for the Fermi-Dirac distribution. At the same time, in a longer time scale, the electron gas will collide and thermalize, but this time it will reach temperatures which can be extremely high. They can be of the order of thousands of kelvins without the particle melting, because this is still a non-equilibrium situation in which the lattice has not yet been involved in the process. And it's only on the picosecond time scale that the electrons eventually transfer a lot of energy to the lattice, and therefore we will observe a Fermi-Dirac distribution with an elevated electron temperature compared to the room temperature. So we are particularly interested in these two processes because, as you can see here, if this is our energy axis, we have the possibility of generating a population of electron or holes that have very high kinetic energies compared to the initial Fermi-Dirac distribution. So because we are also working with nanostructures, now we have an opportunity to collect these carriers at the surface of the nanostructure within their mean free path. And therefore, we can imagine transferring this carrier either to a molecule or to a substrate. So the question you might be wondering is why this is interesting at all and why this should give some advantages from the point of view of the chemistry. And to understand this a little bit more deeply, we have to go back to our schematic of the energy distribution of the carriers and think how this would be transferred to an adsorbate molecule or a neighboring semiconductor. So if we take now a metal, which is a catalyst, as I mentioned you at the beginning for gold and copper in our case, when the molecule adsorbs on its surface, it will create a number of adsorbate states. Typically, in an equilibrium condition, the electrons will transfer to a lowest unoccupied orbital or adsorbate state from these low energy electrons of the Fermi-Dirac population. However, now, if we have a significant proportion of hot carriers with high kinetic energy, we have the possibility of populating highly excited state orbitals, which then would result in a completely different chemical reaction pathway. We also have to think that these carriers, indeed, because it's a metal, recombine very rapidly. And so it can be useful to pair this metal also with a semiconductor. In this case, you see a p-type semiconductor. And imagine transferring one of the other type of carriers into the semiconductor to prolong the charge separated state and reduce the recombination in the metal. So all of these processes together are quite attractive to try to control chemistry, and indeed they have been the subject of intense research over the past few years. And what is interesting is that in a way, these hot carriers can mimic the function of natural photosynthesis that utilizes highly excited state carriers to drive the ensuing chemical transformations. So when we now think specifically about the process of CO2 reduction, what was novel at the time when I started working in this project was that nobody had tried to realize a system where electrons were transferred to adsorbate molecules and holes were transferred to the semiconducting substrate. In fact, typically we have available N-type semiconductors, so it was much more common to transfer the electrons to the semiconductor and leave the holes available for the molecule. However, if you want to apply this concept to CO2 reduction, we need to be able to realize a system which is a photocathode, so the electrons need to be transferred to the molecule. So to engineer and understand this system, I split the investigation into two aspects. I first focused on the metal semiconductor interface, and this was to be able to understand better the properties of hot holes and their collections. In fact, it wasn't at all clear that we would have been able to transfer highly energetic hot holes due to their short mean free path. In a second step, after we clarified this interface, I then proceeded to devising a full photoelectrode and characterize its photochemical response in CO2 reduction conditions. So these are the two aspects that I will be discussing in the next slides, and I will start from the solid state aspects that pertain to the metal semiconductor interface. So as I mentioned, if we want to understand how holes are transferred to the semiconductor, we then need a p-type semiconductor. And also what is important here is that we're interested in generating charges in the metal, so the semiconductor should not absorb any light. Therefore, we need a wide bandgap semiconductor with p-type doping, and there are very limited choices, and our choice fall on the p-type gallium nitride. The second thing we wanted to do was really to combine a highly accurate experiments with full theoretical modeling of both the hot carrier generation, transport, and injection at the interface in order to be able to really understand which type of carriers were being transferred. In fact, when we, in experiments, we measure a photocurrent, we are making an integral measurement of all of the carriers that have been able to overcome the metal semiconductor interface. In order to compare experiments to theory, we also had to realize really clean interfaces between the metal and semiconductor and precisely characterize both the absorption and the photocurrent generation as a function of the photon energy. So for example, here you can see the results for the absorption in gray and the external quantum efficiency of our device as a function of the incident wavelengths. With these two information, we are then able to extract the internal quantum efficiency of the system, which is the quantity that we can more easily compare to the theory. So what you see here are the two internal quantum efficiencies as a function of the photon energy for two different devices, one which is gold p-GaN device and one is a copper p-GaN device. So the first feature that we observe is that indeed, for very high photon energies, we have a steep rise in the photocurrent. This is telling us that indeed for very high photon energies, we have a very large probability of generating high energy hot holes, and that these hot holes then are transferred into the semiconductor, resulting in this very high photocurrent response. So this is indeed telling us that despite the fact that they have very short mean-free path, we are able to collect them when the photon energy is sufficiently high. At the same time, this dashed line showed you what we would have expected for a Fowler injection model for holes with increasing energy. And so the fact that we observed this steep rise at the higher photon energy than initially expected is telling us that indeed there is an intermediate regime where the mean-free path is a limiting factor for the collection of the holes. Subsequently, we wanted to go a little bit deeper to understand better the details of this metal semiconductor interface and the injection process of the holes. So we realized an analogous sample where we now have in large area gold nanoparticles onto the p-type gallium nitride, and we perform ultra-fast spectroscopy measurement. We use a green light pump, and then we use a mid-IR probe to measure the population of holes in the semiconductor. What this transient plot shows you is that very quickly we have a strong rise in the absorption signal from the mid-IR probe. And this rise time is limited by the instrument at 200 femtoseconds, telling us that hot holes inject across the interface at the time which is shorter than this, which is totally comparable to the injection time of hot electrons that had been measured before. Also, importantly, this experiment shows us that the presence of hot holes across the interface persists up to nanoseconds, which is a very important information if we plan to apply this system for chemistry, because chemical reactions typically are slower, and therefore this ensures we have charges available for a longer time frame. At the same time, this is telling us about the fate of the hot holes, but we also wanted to understand more about the fate of these hot electrons that are remaining behind in the metal, and that in a real situation, we would expect to transfer to a certain degree to the absorbed CO2 molecules. So we use the exact same sample and perform a second ultrafast spectroscopy measurement, where now we use a white light probe that probes the population of the electrons and the electron dynamics in the metal. Again, the signal is a transient signal. In this case, it's a pronounced bleach at the plasma resonance and then a recovery time. And the recovery time allows us to extract the electron-phonon coupling time for the system. What is important is that the electron-phonon coupling time depends on the peak electron temperature during the thermalization of the electron gas. So we performed this experiment in two different cases. We had our gold p-type gallium nitride system where we know we are extracting holes, and then we have gold nanoparticles on isolating substrate where we are not removing any hole. And what we observed is that the slope of the increase of the electron phonon coupling time with the energy density that is absorbed in the metal is very different. And it's much lower for the gold p-type gallium nitride. This is a very important information because it's telling us that the electron gas thermalizes to lower temperatures in the p-type gallium nitride system than in the isolating one. So in fact, if you remember, I showed you at the beginning, this is the very prompt distribution of hot electron and holes. Then we know we are transferring part of the holes to the semiconductor, but in a slightly longer time frame, we will have a thermalized electron distribution. And so when we are removing the holes, we know now that we are on this type of curve, while when we are on an isolating substrate, we have a much higher energy. And as you see, this is important because if at this interface we plan to have adsorbed molecules, it means that in the second case, we have a lower population of high energy electrons. So indeed, we have performed theoretical calculations also to demonstrate this, and we have observed that as we increase the fraction of removed hot holes, the peak electron temperature decreases, and from comparison with the experiments, we could estimate an extraction efficiency of close to 90% in our system. So indeed, by these solid-state studies at the interface between metal and semiconductor, we could learn that ultra-fast hot hole collection is possible, that this hot hole removal can create a long-lived charge separated state, which is very beneficial for chemistry, but at the same time, we have a trade-off because this reduces the peak electron temperature distribution if we have a thermalized case. So now let's see what happens when we take this heterostructure and we use it in real applications for CO2 reduction. So indeed, we took an analogous sample. Again, we have these gold nanoparticles on p-type gallium nitride. We inserted in a photoelectrochemical cell, and we studied a quantity reduction reaction of CO2 to CO and hydrogen evolution. And we do this as a function of photon wavelengths, So the first thing that we see is that when we shine light in our system, every time we illuminate our device, we see an increase in the current that is generated. And this is a signature that indeed we are generating, we are increasing the reduction reaction. And as you can see here, the semiconductor without the nanoparticles does not have any photocurrent. We also did this measurement as a function of the photon energy, and the solid red curve is the photocurrent generated, and the light red curve is the absorption spectrum of the gold nanoparticles. So as you can see here, all of the current that we are measuring is originating from the metal absorption, not from the semiconductor, which is different from a conventional photoelectrode system. What about the products then? Well, we measured the generation of carbon monoxide and hydrogen in dark. We have a certain evolution with time. And then we repeated the same measurement under illumination. And although the quantities are pretty low, we could see a 20% increase selectively on the generation of carbon monoxide. And this fact that we only see the enhancement on the carbon monoxide is very important because this is, if you remember the beginning of my talk, this is what we are after. We don't want to indiscriminately enhance all the reaction happenings, but we want to try to enhance specific reactions. So what about a metal which can generate more interesting products, such as copper? We have more recently fabricated an analogous system where we have copper on p-type nickel oxide to maintain the Schottky barrier to reasonable degree. And in this case, we have again performed the CO2 reduction process, and we have observed that 3 different products are generated. We always have hydrogen, we have carbon monoxide, and in this case, we also have formic acid. The blue dots are in dark, and then the yellow dots are in under illumination. And so again, we see that under illumination, we reduce the generation of the hydrogen, and we enhance the generation of carbon-based products like carbon monoxide and formic acid. So again, the presence of these plasmonic nanoparticles entails a system with a selective capability of driving the CO2 reduction reaction over the hydrogen evolution. At the same time, we were not able to observe carbon-carbon products, which is what we were hoping for. And this suggests that there might be other trade-offs between the possibility of transferring an electron to the adsorbed molecule, as well as the inducing a faster desorption, for example, of carbon monoxide, which is the intermediate molecule that is needed to create more complex products such as ethanol. So this brings me to summarize these past results. And indeed, we have shown that by testing this plasmonic photocapsule for CO2 reduction, we have been able to observe enhanced selectivity for carbon-based products against hydrogen evolution. But still, there are yet many open questions in this field that need to be addressed. And I think the use of photonics and nanophotonics is going to be playing an important role, because we have to be able to improve our capability of controlling the properties of these plasmonic nanoparticles during the chemical reaction. So in fact, to understand and improve our control of the selectivity, in our group, we have started to develop highly controlled micro-scale photoelectrochemical studies of this reaction. And at the same time, we can also use photonics to go towards engineering high surface area and highly absorbing photocapsule for CO2 reduction, where we can generate products in larger scale and therefore have a better chances at analyzing these complex devices. And this is indeed something that we have already had some preliminary work on in my group. In the first year, we have developed a hierarchical ultra broadband absorber. This system is fabricated with scalable synthesis technique, and it combines light trapping from a forest of copper nanowire with the high absorption due to carbon nanotubes that are grown onto it. With this, yes, I'm coming to conclusion. Okay. So this allows us to have this very high absorption, and thanks to the presence of a small copper nanoparticle on the tip of each of these carbon nanotube, we hope that this hierarchical absorber will be able to give us interesting results in terms of the CO2 reduction performance. With this, I would like to thank some of the collaborators, in particular Joseph Duchenne and all of my team, and in particular Fatma Kiani at Zulus, who have worked on this absorber. Thank you very much.
Thank you, Julia. Thank you for your talk. Okay, now the talk is open for questions from our judges.
Thank you. Very nice presentation. I have a quick question on the potential oxidation and its impact for the lifetime of these plasmonic CO2 reduction systems. Can you comment on how you see some of those practical challenges to be addressed?
Yes, this is a very good question. So one of the advantages for the CO2 reduction aspect is that it's a reduction process. So typically, we do still need to apply a little bit of a negative bias to the electrode to be able to drive the reaction. And this negative bias has already been shown to be sufficient to re-reduce any kind of oxide that might have formed, especially on copper. I mean, this is more than gold. This is a major issue on copper. And we know from other experiments from other groups and our own experiments that the oxide layer can be re-reduced back to native copper.
Julia, very nice talk. And so could you comment on the hot carrier photodetectors? The quantum efficiency of these detectors seems to be not so high. And so would you like to comment what are the limitations and how you can improve those ones?
Yes, thank you. Very good question. So I want to remark that in my experiments, I wasn't after the performance of the device, because my focus was on the perfect control of all of the properties at the interface and the structure and the shape, so that we could very easily compare with the theory through numerical calculation and ab initio calculations. Said this, we know that the low internal and external quantum efficiency we obtained were primarily dictated by the low injection probability at the metal semiconductor interface. And in fact, there are strategies that can be used to mitigate this issue, which arises primarily from the momentum matching between the carriers in the metal and the semiconductor states. So in this respect, roughening the interface can help, and also embedding the particles and shrinking the size of the particles are all aspects that can benefit the performance. Nonetheless, there has not been reports that are able to show, at least for the visible regime, that can go much beyond a few percent of efficiency. And this remains a big open question in the field, compared to the high extraction efficiencies that we see from the ultra-fast spectroscopy experiment. What I showed you in our measurement, we estimate 90%. Measurements on the hot electron side estimate 50%, but no steady state device has been able to approach these values. So this is a major challenge to be clarified.
Okay, thank you. But as a follow-up question, for the CO2 reduction, challenge has always been the efficiency of the reduction process. And would you like to really comment on that one? Because with respect to the hydrogen generation using water splitting, and the CO2 reduction has been much more challenging. And would you like to comment on how you can really be able to enhance the reduction efficiency?
Yes. So for the reduction efficiency, there are a lot of strategies which are similar to those of the hydrogen in terms of, especially in improving the photonic aspects of the electrodes, maximizing the absorption and the charge generation. If you have a semiconducting electrode, obviously the balance between surface area and charge recombination is very important. I think for the CO2 reduction, as I mentioned at the beginning, the real major challenge is more than on the overall efficiency at the moment. It's really on the selectivity, because the problem is that, for example, copper can generate carbon monoxide and ethylene, but at the same time ethanol, which is liquid. And so now you would need a humongous amount of energy to separate these products. And this would completely wash out the advantage of being able to do CO2 reduction in the first place. So the challenge of selectivity is really what is preoccupying most of the community at this stage.
Okay, thank you.
Okay, any other question?
Okay, maybe I'll ask another question. And people are also interested in trying to create syngas from the CO2 reduction. Would you like to comment on how your plasmonic structures can help in creating syngas?
Well, that could be another way. I'm not sure there have been reports in that respect. That is more of a high temperature process. So there could be some advantages related to the local photothermal heating that can be obtained with plasmonic nanoparticles that we know can be very strongly localized temperature at the nanoscale. And because they're also the catalyst, now you are able to selectively heat up the catalyst without having to heat up a huge, bulky heating system. So this could also be, going forward, an application of these plasmonic systems that overcome some of the challenges of macro scale devices.
Okay, good. Thank you very much.
Very nice talk, Julia. I have a question about the ultra-fast spectroscopy of plasmonic heterostructures. So will the plasmonic resonance or the shape of the plasmonic structures or the shape-dependent plasmonic resonance affect the results, or how the effects are?
So not exactly in terms of the overall behavior. So I would expect that we would still observe a very fast rise of the signal and a relatively longer decay of the nanosecond time scale. Definitely, it's gonna impact the efficiency of the extraction, because depending on the photon energy at which we have the resonance, we can have higher or lower energy of the carriers compared to the Schottky barrier. And so if we go too long of a wavelength, we will basically not be able to transfer carriers for that reason. So that is definitely going to be visible in the signature, but not so much in terms of the other types of properties of the signal that we see. I'm not sure if I completely answered your question.
Yeah. Good.
And the roughening by bringing in different orientations of the crystal at the interface then enables more of the coupling between the metal and the semiconductor. Yet I think this is the other, let's say, this is the real open question of understanding exactly this charge transfer at this interface, because again, I think we really need more support from the theory in understanding really at the atomistic level how this charge transfer happens between the metal and the semiconductor. Because again, these Schottky barrier models are still very approximate, right? I mean, you're just ignoring all the real details of what is there in the interface.
Great. Okay.
Thank you very much.
Yeah, the time is right up. So thank you again, Julia. Thank you for your talk.
Thank you.
Thank you. So that concludes our presentation and the questions part of today. We will continue with panel discussion and then following with awards ceremony. So please stay with us. We thank all the speakers and also thank all the judges and also thank all the audience to stay with us.
How did you think about this event, and how about your ideas for the innovation and with others? Did you have anything? Yeah, please, Amit, I see you. Yeah, can you go ahead to be first one say something?
Absolutely, yeah. First of all, I would like to thank Light Science and Applications for taking this initiative to support young researchers like me and many others on this screen. And it's really encouraging for all of these young scientists, both to be in a panel and to listen to each other in this tough time, but also share the stage with these luminaries that were judging the talk that we always look up to. So thank you again for providing this opportunity. And not only did I learn, share some of the stuff that I have done, but I have learned quite a bit from all these top research going on in various directions, from optical trapping to solar fuel cells to integrated photonics to frequency combs. So it has been quite a fantastic experience for me, and I appreciate your efforts towards making this happen. And I thank all the judges for their time. It's quite a remarkable dedication on their part. So I thank them again. Yeah, that's all I have to say. Thanks.
Okay, great. Yeah. Julia, I see you're still there. Yeah. So your wonderful talk. Well, we all love that. How about your feeling?
Yeah, I think it was, I have to second Amit's comment. I think it's been an amazing experience, and it's always very empowering to be able to share your work and to see other great works from colleagues and hopefully friends. So I think this is really a good opportunity to make connections and maybe create more collaboration in the future. So I think this has been really a fantastic experience.
Okay, yeah, competitors, also friends. Maybe future is collaborators, right? Exactly. We are proud of you. Julia, you are the only female on the stage. I'm so proud of that. Yeah, you did a wonderful job. Yeah. So, so young. Yeah, nice to see you again. Yeah.
And nice to see you again.
Yeah. So, how about you? How about your feeling? Yeah.
It's really fantastic. It's really provide a platform that we can learn each other. The only downside is that it's too early for me. I mean, so I still feel a little bit sleepy. But it's great event that I learned so much from the colleague. Hopefully, in the future, become friends. And also, I want to comment on one of the questions from Amit, that Judge asked you the super resolution from metasurface. So I would say that if you can couple the metasurface with the lective index soft metamaterial on top, that will give you high K immediately on the surface. So that will eventually generate high resolution, super resolution imaging. So that's one of the things that we can easily utilize this soft metamaterial that in the real application for the imaging. Hopefully we can discuss more with all of these fantastic colleagues and become friends eventually. Thank you. And thank you for the organizer and all the committee.
Okay, cool. Yeah. So are you already in Arizona?
In 1 month.
In 1 month.
In 2 months, actually. Yeah, in December, I will move there.
Okay, congratulations for your new job. Yeah.
Thank you.
Yeah, so Yang Yi, are you still there? Yeah, could you turn on the cameras? Let me see you. Oh, no, hopefully not. Yeah. Okay, Junqiu, yeah.
Yeah, I mean, I think it's a lot of fun actually, especially during this critical time. And I have to say that actually, I feel that actually everybody is really high level and talk is really good. And for me, actually, I broaden my scope and my knowledge in this kind of online workshop. Actually, I learned a lot, and I found it's really cool. And I would be even more interested to have it next time in a lively kind of presentations. And then we can face discussion, and probably even afterwards we can have something goes into some technical details. That would be a lot of fun. I have to say that I really like this kind of way to bridge people together from different fields in photonics, optics, and it's really enlightening and educative for me actually.
Okay,
Thanks.
thank you so much. You see that this platform is interesting. Yeah, for sure. We during this COVID-19 time, it's really hard for everyone to meet face to face. But yeah, in the future, I think we will meet. Yeah. Okay, Miguel, I see you there. Yeah. So yeah, it's your time to get your group.
I'm sorry, Alice?
Hi. Yeah, now I think you can host the, last week's speakers to say something about this during our
Sure,
waiting.
sure.
Yeah.
Sure. So thanks, Alice. It's been really inspiring to listen to all of the research presentations both last Friday and today. I wanted to say that the mission of these talks is to connect the world and the universe. And so we heard from Alice at the start that these talks have been connecting the community for a few years now. We should not forget that this event and any online activities are actually enabled by advances in optics and photonics over the last decades. That includes, of course, optical fibers and fiber amplifiers and modulators and detectors and related technologies. And so perhaps when we meet again for this event in a few years, further advances in optics and photonics will enable the event to be in some sort of seamless virtual or augmented reality. I'm really excited to see what Alice will do with these future advances. I think it will be amazing. And so the questions that I had for the panel, and after this anybody can go first, is kind of answer one of these two questions. First, in terms of the online experience from things that you learned in 2020, of course, from this event, but also from all of the remote work that you've all been doing. What have you learned? What are you going to keep for future years? And then secondly, what advances in optics and photonics are you excited about that you think will enable the future of working or gathering remotely? So anybody from last Friday, do you want to feel free to start?
Maybe I can start by saying something small. Thanks, Michael, for those wonderful questions. I believe my learning was that since we all work on light, anytime we are in an online conference or event with the camera on, lighting itself is very important. So you have to plan in advance and make sure everything is already planned beforehand so that we have a very smooth experience. But also I'm very amazed by how much the technological world has been able to support this huge upsurge in demand over video conferences or Zoom and everything else. And going forward, I believe I'm excited about a couple of technologies. Of course, the traditional ones such as higher speed modulators or increasing bandwidths, but maybe things like Li-Fi with information being strobed directly from LED lights that are modulated at speeds that we cannot see overhead could make things even smoother and faster. And as you already mentioned, the virtual reality, augmented reality experience. This was one of my first experiences with AR, VR. So thanks, Alice, and the whole organizing team for organizing this. And I believe that it can only get better from here. So yeah, thanks to everyone and the whole panel. And I really learned a lot from the various speakers from a huge breadth of topics. Thanks.
Thanks a lot. That's great.
Yeah, so if I can jump in for a sec, this is Shuo here. I'm from Gila and CU Boulder. Yeah, Mikhail, nice to meet you. I think unfortunately, you missed my talk. I'm the first talking last week, but yeah, that's fine. Nice to meet you. Yeah, I would like to thank you and also thank the organizers, especially iCANX and Light Science and Applications, for hosting these wonderful events, especially to support the young scientists at this difficult time of the whole world. Speaking of the questions that Mikhail brings up, so I'm always kidding to my colleagues that because I started my assistant professor position this fall semester, so I'm always kidding to my colleagues that maybe we are just becoming the new generations of professors who get used to Zoom teaching. And we are probably the generation that when we need to switch Zoom teaching to in-classroom teaching, we need to readapt ourselves and readjust ourselves, because they are always talking about like how difficult or the challenges they are facing with switching from in-classroom teaching to Zoom teaching. I'm like, okay, this is my first class and I'm teaching with Zoom, and I don't feel any extra difficulties because I just feel like this is a new class and I need to learn everything. And maybe I will need to see a lot of challenges hopefully sooner when I switch from Zoom teaching to in-classroom teachings. I think a lot of techniques that I learned from Zoom, from using the Zoom technology, from all this online teaching, is very helpful. And I think nowadays people realize that although we cannot really connect face-to-face very easily, but in some sense, I think we are better connected. This event is a really good example of how actually these people from all over the world, I know someone already probably 2 a.m. in the morning, very late, and someone has to get up very early. But anyhow, we are able to connect globally and in this event. I think in some sense, this pandemic helps us to actually better connect, and we should really keep a lot of virtual events in the future, even when the world recovers to its normal state. Yeah. And in terms of technologies, I think, yeah, definitely a lot of vision technologies, light technologies like VR, AR will definitely further facilitate human interactions in the future, hopefully. But I think it's also important that we need to combine all these visual technologies with other technologies like mechanical sensors and all these things to get like a better feeling in terms of human interactions, like how to track your eyeball movement. And because our interactions is not just to see each other, but it involves a lot of other feelings. So how to kind of incorporate a little bit other type of feelings into these human virtual interactions, I think can be a very interesting topic, although this is not something that I'm working on. Yeah, that would be my a little bit ideas here.
Yeah, thanks a lot. Actually, many years ago, I remember visiting the MIT Media Lab, and they had like a gizmo with these 3 rotating cylinders where you rotate them on one side and they rotate automatically, somewhere else. So there's kind of a pair of them, and so you could like shake somebody's hand, for example. I'm surprised that in the pandemic that hasn't become something like that hasn't become more common, where you have some tactile way to say hello or something like that. So I think those are really wonderful perspectives. Thank you. Who's next?
Well, I'd like to jump in. Well, good day, everyone, and it's a real pleasure to listen to several exciting talks this morning. So I'd like to thank the organizers for this very wonderful event. I think it's a very terrific experience for me. I've actually gone back to listen to several iCANX talks in the past, and I think there's something that one has to keep on doing to continue to educate ourselves on the latest advances in the field. With respect to the remote learning experience, I was quite impressed to see how you can have people stay like on a stage like configuration and giving presentations based on this Bedu platforms. I think that is really wonderful. Some important advances that I think would be beneficial in the future would be really having more advances in the AI and bringing that into the domain of remote learning. I think Zoom is already doing a lot of that, and of course, Bedu. But one thing I noticed, like when I went back to listen to the past talks, sometimes the translation of the languages, was not actually perfectly correct. Some sentences were not perfectly translatable. So, but I think with introducing more of the AI, more advances in AI would help to.
And maybe I can jump in. Hi, this is Guang Wei from National University of Singapore. So I think this is really a wonderful event, and I actually learned a lot during this process. So, and I would like to thank the LIDAR and also the committee for hosting this event. And for me, this online conference is, I mean, for me, everything is new. I seldom go to conference. This is probably maybe the second or third time for me to go to the conference, and but now it's an online conference. I don't know. I mean, I don't know what is the experience for the on-site conference, the real conference. But anyway, I really like this online conference, and I also listened to several other iCANX talks. And more importantly, I feel really honored to see my names among those brilliant scientists. And actually, I learned a lot from their presentations. And for me, regarding to the future technology about the photonics, I think the most important thing is to develop the new materials. And every time when you say you are going to control your light, you need to take care of the light-matter interactions. So I think one of the future directions is to bring more materials to this platform, like the 2D materials, and the metamaterials, the metal surfaces. And those platforms are very great. And more importantly, for the 2D materials, which I'm working on, so there are a lot of different physics. You can use those new materials to build up the new multi-physics optical materials. So with that, you can control light for many other important technologies. And I'm more curious about the new materials with the new physics. So with that, yeah, thank you.
Yeah, thanks a lot. I mean, I think your point about conferences is very well taken. There's some people that here, in this kind of virtual room that used to go to many conferences every year, and others who, it's harder, either for practical reasons, like visa issues and family issues and many others. And so this is kind of a democratization of knowledge and of visibility, and I think that's really wonderful. Let's see. Shulin?
Hi. Hi. Good morning, or good evening, or good noon, everyone. I'm very happy to join this online workshop, and I'm Shulin Sun from Fudan University in China. And we know that it is a very hard time for every people in this world. And we can only join this workshop online, and we cannot do our presentation and contact with each other face to face. However, we can it become more easy and more efficient to discuss with so many new friends and old friends, and we can just use a computer and connect to the internet and do our presentations. And we have so many very great talks and so many very exciting works, and I learned a lot from all of you, and I'm very happy and very honored to become one of one of you, and thank you very much.
Wonderful. Thank you very much. Alice, how are we doing?
Yeah, we're waiting for the final results, but yeah, not come out yet. So yeah, we still have some time. Just now we miss Yang Yi. Yang Yi, you relog in. Yeah. So yeah, could you turn on your microphone? Yeah, say a few things about your feelings for this, competition.
Sure, thanks. Yeah, so I apologize everyone. I saw that just now there's some closed door discussion of the judges, so I just log off, but later learned that we should log on actually. Yeah, I mean that's it's such a pleasure. I mean to attend this online event. I mean it's based on my experience. I think it's so important that you can have chance to interact with your peers and to establish collaboration. And the best is also a personal friendship. I mean I know a few guys here like Avik from Stanford, so we talked a few times, and I think it's really nice that everyone here can demonstrate their research. And I learn a lot, by attending your talks. I mean, I really hope that, we can discuss more offline and to establish collaboration. I think that's something I think is very important based on my experience. So, and especially with your peers. So in that regard, I thank the committee and as well as this iCANX platform for us to be able to do so. Thank you very much.
Okay, cool. Yeah, so yeah, we got your. I hear your talk. Very nice talk. So Guangwei,
thank you.
I didn't hear anything from you. Are you ready?
Actually, I just expressed my opinion.
Oh,
but,
really?
yeah.
Sorry. Maybe I missed something.
Okay. Nevertheless, yeah.
Okay, it's nice. And we looks like we still wait a little bit time. I didn't get the final result. So
I just right now sitting in my office, but I can talk with all of these excellent researchers all over the world, like three at Berkeley and in MIT. So yeah, I think it's a wonderful platform for everyone. I like the vision from Alice, connect the world, make the scientist the superstar. I think today all of them are superstars. I think no matter the final awards go to whom, but for sure all of them are the leading stars in the field of optics and photonics.
yes, it is great. Yeah, you remember, for iCANX, what are we going to do? We're going to have, promote science as a fashion, promote the scientists as superstars. I think now on the stage, everyone already did that. Today we have, 270,000 audience online, so waiting for our results. So I feel excited too. Yeah. Yes, I saw Professor Chiu. Are you there? Yeah. So could you give some comments or reviews for all this process and this event? Yeah, they're all waiting. Okay. So now
Yes.
online. Okay, cool. Yeah, please.
Sure. And this is truly a great event. I did enjoy 2 wonderful nights with all the 10 presentations, and they are all really wonderful rising stars in the field. And actually, many of their papers I read before, and it's very refreshing also for me to listen directly from their talks. Of course, I also met some of them in different conferences. As some of you said, it's truly a pity that we cannot meet in person during this 2020, but somehow we can still survive with Zoom meetings and others. And I also did lots of teaching with Zoom and also participate in several conferences and give lots of talks through internet. So maybe it's we will probably get used to it in future. And then we can spend more time with family and with our friends and to do something different. And I hope the technology will be even better in future, that we can somehow be present both in the place for the conference and also at home. Is these candidates for the rising stars are extremely good, and they also did great job.
I saw that. Yeah, so the result is coming in my folder.
Oh,
so,
great.
Yeah, just waiting a moment. Yeah, I see everyone was nervous on this. I saw your face. Okay, yeah. So, Bobby, relax. I still need, to download and then share with you. Okay. Yeah, hold on 1 second. It's coming. Yeah, reading on that. Let me see. Okay, if I'm got it now. Oh, I already see it coming. So, yeah, you feeling exactly right. Actually, since this spring, I think a lot of people was talking about this. What's going to be future for teaching, for even for the communication, for our conference, where I'll go. Yeah, we will get used to something online, get to something, we can communicate much more convenience, and we save some time, save energy. And even we can save, a lot of time, a lot of money for traveling, on different part of the world, Yeah, that's truly a big issue for everyone. Yeah, so let's see. It's coming down. Oh my God, it's almost there. Okay. 20 seconds. Please wait. Yeah. So one thing I have to say at the very beginning, now everyone, please turn off your camera. Once I announce your name, you turn on your camera, okay? Please, everyone, turn off your camera. We keep secret, okay? Yeah, please turn off your camera. Yeah, so for all the jurors, you will get on board to, deliver the word. And Duncan, did you want to say something before I, read all the results?
Sure. I think this has been a very exciting 2 days with excellent presentations from junior researchers from all over the world. I think I really enjoyed it, and we should repeat this again. And the results, I know that they're reflecting the quality and the excellent research potential impact of what they have presented. I think all the 10 presenters are truly winners. Unfortunately, we could only select 6 of them in the form of the first prize, second prize, and third prize. So I would like to again congratulate every one of those 10 speakers, presenters, for their excellent research and how they communicated these difficult concepts, difficult to explain concepts in 20 minutes with such excellent presentations. I'd like to also thank all the peer committee members who spent valuable hours judging these young researchers, and I think overall we've done a great job to narrow it down to the final winners, which you will soon announce, I hope.
Okay, Duncan, I see you have gone through some hard time. Yeah, your voice was, yes. So I will announce that everyone can see my screen. Can you see my screen? Okay,
Yes.
I already shared that. Yeah, so that's the 10 finalists. Yeah, get on all this stage in these 2 weeks. So Yeah, I gave you, let me see what happened here. Okay. Yeah, so that's what we done in last 2 weeks. I think all of you, see all this lovely face and everything. Everyone have pictures later. Okay, don't worry about that. I will give you the words right now. So be ready. Yeah, be ready. Yeah. Okay, that's a 10 finalist award. Yeah, everyone has a certification. We will send to you. Yeah, just all the 10, finalists. Don't worry, everyone have at least a page, yeah, for the certification. So we will send to you. So first we came to, yeah, Renmin, are you there? Please turn on your camera. Yeah, let me see you. Yeah, okay. Yeah, the first I will give you the chance to announce for these 2 candidates awards. Okay. Yeah. So see that. Okay, please. Could you see that? Yeah.
Okay. So the candidate awards goes to Lin Sun from Fudan University and Guangwei Hu from National University of Singapore. Congratulations.
Okay, congratulations. Okay, Guangwei and Shulin, yeah, you got the candidate awards. We have another candidate awards. Okay, Michael, yeah, are you ready? Turn on your camera. Yeah.
Ready.
So, yeah, so
Yeah.
it's your turn.
I'm stressed. You can hear it in my voice.
I can hear you. Yeah, so, yeah. Okay, so we still have another 2 candidate awards. So it's your turn to read their names. Okay, yeah, here it is.
So it's my great pleasure to announce that the candidate awards go to Yi Yang from MIT and Sui Yang from the University of California, Berkeley.
Congratulations. Okay. Now we came to the 3rd award. I will announce the first one. Okay. The third award goes to Avic Dot, Stanford University. Please turn on your camera. Let me see you. Congratulations.
Thank you. Thank you very much.
Okay, yeah, wonderful job, wonderful speech. Okay, the second, 3rd awards. So, Andrea, are you ready to announce that? Andrea, let me see you. Yeah, so, no?
I'm here.
Okay, yeah. So, Andrea,
The-
please. Yeah.
The
So,
next,
goes to, okay.
Justus Duquaife. Congratulations, Justus. From Vanderbilt University.
Yeah, Justice. Yeah, we see your lovely face. Okay, congratulations. Okay, yeah. The third one, the third prize, Professor Chiu, are you ready? Yeah.
Yes.
Yeah, okay. Yeah. Chiu, please, this one.
So the final 3rd prize goes to Junqiu Liu from EPFL. Congratulations.
Yeah, Jun Chiu, congratulations.
Thank you very much. Thank you.
Okay, cool. Now we came to the second prize. We have 2 second prize. Okay, the first one, Professor Jagdish. I see you there still very, looks very energetic, not feeling the sleep. Okay, yeah. Okay, the second prize, the first one goes to.
Second prize goes to Dr. Amit Agarwal from NIST. Congratulations, Amit. Well done.
Okay, yeah. So, Amit, are you there? Oh, nope. Oh, good. Yeah, your lovely face. Cool. Congratulations, Amit. Yeah. Professor Cao.
Yes.
Yeah, we will announce the next second prize.
Yeah, the second prize goes to Sun Shu, University of
Colorado. Yeah.
Colorado.
Yeah. So, Shuo, are you there?
Yeah. Sun Shu.
Yeah. Turn on your microphone,
Yeah,
please.
this is my honor. Thank you very much.
Good job.
Very great. Now we have the last first prize. And Duncan, it's your time to,
Sure. I think everybody knows the winner. Because it's the last one. Dr. Julia Tagliabue from EPFL. Congratulations for the first prize and the excellent.
Okay, yeah. Julia, please turn on your microphone. Yeah.
Thank you very much, everyone. I'm really overwhelmed. It's a honor and a pleasure, and yeah, I'm speechless. Thank you. I'm very grateful.
Okay, great. Yeah, I think this week we really have a lot of surprise. Just now you see everyone. We try this on-site and online conference go together, but it's getting very smooth, very good. So congratulations to everyone, and thanks for everyone. And I hope you keep looking for iCANX talks. Next week, we will go to discuss for what's the future for the communication of academic. So the society, I hope, and Dugan, we will stay on the stage. We are talking about that. So next week, I see you on iCANX talks. Congratulations to everyone.
Congrats.
Okay, great. Yeah. Okay, see you next week. Yeah, next Friday, 8 o'clock, Beijing time. So thank you.
Hi, everyone.
Thank you.
Congratulations.
Yeah.
Thank you,
Bye.
everyone.
Congratulations.